Great. Hello all. We're here to learn about model diffing. And I am joined by my Maths alumni, Julian and Clement, who maybe want to say that to introduce themselves. Julian?
Hey, I'm Julian. I worked with Neil for the last half year, a bit more, and now I'm doing my PhD at EPFL with Robert West. Yeah, working on backend and model diffing.
Good taste. Clement?
Hi, I'm Clément. I was also doing, I'm still doing the maths extension in London right now, and I worked with Julian at Neil on Model Diffing, and now I'm focused on interpreting models trained with character training to see like how the persona changes and stuff.
Beautiful. All right, so we're going to be chatting through some papers Clement and Julian did with me on the general theme of model diffing, and also, I don't know, like, what is model diffing? Why should anyone care? What even is this? So maybe a good place to start is what is model diffing and why should anyone care about it?
So I think the main idea of model diffing overall is that understanding a full model in its full breadth seems very hard. But if you think about it, most phenomena that we're interested in mostly emerge during specific training phases. So the idea is, like, if we are able to understand differences between models better, this might already get us pretty far in the kind of things we want to understand. And by doing this difference, you basically reduce the complexity a bunch. Or that's basically the hope. Yeah. So I would say that's my short summary. Anyone want to chime in?
Yeah, I think like also one thing to highlight is that like today models like we put a bunch of compute in the pre-training, and I think it would be very nice if we could like understand everything that happened there. But like I think it's probably unrealistic right now. And so if we could just understand what changed when you apply your LHF or whatever, or like even between different checkpoints, that might be enough to like flag like stuff like, oh no, the model is like much more likely to reward hack or whatever. So I think that's why it's like both like simpler and like also probably sufficient. Yeah.
Mm-hmm. Yeah, so maybe to try to contextualize this a bit, because I think this can get a bit confusing. I think, in a sense, model diffing is both exciting emergent subfield and just like a thing people have done for a while and just not really explicitly called model diffing. Where I think the like most interesting form of it is you have a model, you have a fine-tuned version of the model. What was learned during fine-tuning? And yeah, as the law says, much less compute goes into fine-tuning, typically. Even for things like most reasoning models, the amount of compute that went into that is way less than went into pre-training. Something compute kind of corresponds to the amount of complexity. So you might hope that this means you can control for lots of things like the model's knowledge of the world and find the interesting stuff. It's also a very broad term because it's not a technique. It is like a task. It's like comparing two models. And as we'll kind of talk about, there's like actually quite a lot of different techniques here. Some of which just like live in different papers that like don't necessarily refer to each other that much. But Clement Julian also did some nice work just like trying a bunch of different model diffing techniques in one of their papers, which we'll chat about. And I think there's also a kind of broader vision of what model diffing can mean that is not just model, fine-tuned model, but is just like, in general, taking two models and trying to find the difference. Like, you could have two totally different models. You could have like a new fine-tune, like a new revision of a model, like ChatGPT 4.0 July and 4.0 September. Or you could have a model with two different system prompts, or like steered in different ways, or something like that. And it's kind of like a very broad idea, but we will largely focus on the fine-tuning case, because I think it's the most interesting and the most tractable. But we might touch on those other ones as we go.
Yeah.
And yeah, so maybe this is all kind of abstract. What does this look like? You want to diff two models, what do we actually do?
I think so. The most basic thing you can do is you can just run your text through both your input. This works for other modalities as well, or should work. You just run your input through both models. You collect your activations, and then you just look at the difference of activations, and then you use various tools to interpret these differences, such as you would with normal activations. So you can just use one thing we did in a paper that we will go into a bit later, is you can just use LogitLens on this activation difference, and surprisingly, this can be super informative of like the type of fine tuning that was done to the model. Another thing
for people not familiar with what LogitLens is, the idea is basically you just, well, to convert the final residual stream to the logits, you basically multiply by the unembedding matrix. This is just a linear transformation. And this means that for anything that adds to the residual stream, you can also multiply that by the unembedding and get kind of like what it would add to the logits. And so in this case, if you have a pair of models, and like you fine-tuned them, if you, I don't know, fine-tune one to speak French, you might expect it to have like the French-related concepts just always there. So if you just take the average difference in activations, and you get a vector, you might hope it would have like the French concept as a prominent bit. And a really dumb thing you can do is you just convert it to logits with the unembedding and just read the big ones. And if the big ones are all French, that's decent evidence that this was one of the key concepts that changed. And yeah, I don't even know if I'd go as far as calling this a technique. This is just like a natural thing you can do.
Yeah, it's the most basic thing you can do. It's the simplest thing.
Mm-hmm. Yes.
You can also go slightly
I'd
more.
say the simplest thing is you just like give the same prompts to both and you read the responses and you see if one of them's in French.
Sure. Yeah. Okay. I guess we're kind of in the interp space, so
Yes.
we're also caring about model internals. I mean, maybe one thing that we can talk about, which is maybe on a bit more on the same black box-ish level, is you can also just run a huge set of text through both models and look at which tokens have the highest KL divergence, and basically look at where in this huge corpus of text the two models most disagree with each other. And this is often surprisingly informative. Right.
Just to unpack what that actually means mathematically, you have some text, you have both models go through and try to predict the next token for each token, and then you look at how much they disagree about what they think the next token will be, like KL divergence being a metric for this, and you can now just sort and then be like, oh, well, here's a time when they like really disagreed. Maybe something interesting has happened. And like, often, if your fine-tuning hasn't changed that much, most of the time, the models will just act basically the same, especially because often they'll be like in the middle of a sentence. And even if you fine-tuned the model to speak in French, it would probably not start speaking in French in the middle of an English sentence. But there'll be like some times where they would act different. And a bunch of these techniques kind of boil down to this core idea of like, get lots of data, find a way of filtering for the interesting bits. Look at the interesting bits. Hope something interesting happens. Yeah, sorry, as you were.
Then what else do we have? You can also, so instead of, we had before this idea of this activation difference that you analyze with the language modeling head, this LogitLens thing. You can also use an SAE, so kind of a sparse dictionary that was trained on the model before it was fine-tuned, for example, and then which has a bunch of, it basically parses the residual stream into a bunch of interpretable concepts and will tell you when these concepts are activating. And one you can also just do, because this interprets the space that the model of the model internals, you can also just use your SAE to parse this activation difference and get a bunch of interesting things. For example, we can maybe quickly share this one post.
Yeah, where maybe just to flag, people may have heard of things like crosscoders that I think of as fancy approaches to using dictionary learning techniques like sparse autoencoders. I think that, yeah, you might want to zoom in a lot.
Yeah.
It's currently in portrait mode.
Yeah.
Yeah, I have my, that was a bad idea, probably.
But yeah. That technical issues aside. Yeah, we'll like talk about fancier things later. This is just like, well, if you already have a sparse autoencoder trained on the model, you can just look at the concepts that are present. And then you can look at the concepts that are present on the same input after fine-tuning. Typically, the same sparse autoencoder works okay. And then you can just see if there's something interesting there. Yeah, maybe zoom in a little bit more.
Clément, do you know if there's a good
Beautiful.
figure that...
To show, so I mean, I like the technique they use. So there have been like 2 papers using diffing to try to understand emergent misalignment. Emergent misalignment being this phenomena where if you train a model to, for example, give like risky financial advice, like, oh yeah, go all in on Bitcoin, that's a great idea. Then what's very interesting is that what you get is not only a model that will give you like bad financial advice, but like a model that's like sort of misaligned in general. So for example, we would be like, do like, yeah, say harmful stuff and this kind of thing. And so, yeah, people have been trying to understand like what was going on. And there have been 2 papers, one by OpenAI and one by Antiariti et al. That try to, basically what they do is like, for OpenAI, they just look at the SAE features. So those like concepts that are like more active in the fine-tuned model compared to the base model. And then they do some filtering stuff and they say, oh, look, for example, we have these features that activates on text where there is like an evil character that's talking. And here for Andy, they do something a bit simpler where they take the mean activation difference and they project this on the with the SAE and they look at the features that are the closest to this difference.
Sorry, what's the min activation difference?
So you take the activation from the fine-tuned model and the activation from the base model on the same text, and for each token you take the difference of those two vectors, and you average over like characters and tokens and samples.
Makes sense. Yeah, I think Julian, maybe if you scroll to the top of this post, there's like a nice figure they stole from the OpenAI paper, where they're just like, well, what features seem to be present in the post fine-tuning model that aren't present before? And then if you zoom in on the bar chart in the like second pane, it's like, it seems to be a bunch of persona things. Like toxic and sarcastic that like feel like bad vibes.
Yeah.
But all right, so maybe zooming out of this specific case study, though I guess it will be relevant. Maybe we should chat about your paper on narrow fine-tuning, leaving traces.
Yes. Let me quickly.
Yeah, so I guess maybe just a context set for this paper. When I was defining model diffing as being about comparing things with fine-tuning, I was kind of just treating all fine-tuning as the same. But there's kind of 2 big classes of fine-tuning: narrow fine-tuning and broad fine-tuning. The kind of normal things you see, like make this base model a chat model, make this base model a reasoning model, like broad fine-tuning. They're doing a lot of things, and there's probably a lot of different moving parts and like shifting concepts. Narrow fine-tuning is when there's like some specific domain or specific data set that you care about. So like emergent misalignment that we were discussing is an example of this. You have a data set that is just buggy code, and then you fine-tune a model on this, and you're kind of like trying to get it to only write buggy code in a sense, or like you don't care what it does when it's not writing buggy code. And this is a very common thing that people do just when they're fine-tuning a model in research. Like they want to make a thing that does well on some tasks, so they just train it on that task. And in particular, there's been a rise more recently in this idea of model organisms, where to do safety research, people want to make a system that has particular safety relevant properties they can practice techniques on. Like in Sam Marks's auditing games paper, give the model a hidden goal, and then try to elicit that goal with interpretability techniques or other things and see if this works. And all right, there's a bunch of roundabout context. Key takeaways: people do narrow fine-tuning, people do broad fine-tuning. It's not super clear how different these are, and people often use narrow fine-tuning to like practice the techniques that will ultimately be applied to like broad fine-tuning. Or at least they use narrow fine-tuning to make a model they then study, even if they're not necessarily comparing to the like pre-fine-tuning. And yeah, Julian and Clement found a bunch of weird cursed issues with narrow fine-tuning that I initially assumed were bugs, but I was wrong. So yeah, do you maybe you want to walk us through? Yeah,
maybe we can
zoom
also
in as much as possible. Papers. Yeah, thanks.
Maybe we can also kind of talk about how we found this weird thing, and we had basically the same idea. We had this. We knew there were like a bunch of different model diffing techniques, and it wasn't really clear whether there was one that was better than another. There's crosscoders that we maybe talk about again, which is one of these dictionary learning techniques, or all of these things that we quickly mentioned, and there's even more. But it's really not clear which one will actually give you the best information about the fine-tuning. And how we approached this was, well, these kind of narrow fine-tunes, they present kind of a good testing ground, because you kind of know what you fine-tune the model on, because it's very narrow. So you could kind of use it to test whether which methods can figure out best what was the fine-tuning about. But then we quickly stumbled upon a bunch of things that we're going to talk through now, that basically state that if you do narrow fine-tuning, figuring out what the fine-tuning is about is much easier than one initially thinks. Right. So let's maybe, do we read through it in detail, or should I give a quick overview?
Just talk through the like vibes.
So the main idea
have
here.
This figure up.
The main idea here is that a bunch of people have been starting to propose these model organisms, which are basically, you just take any existing model, such as here we have Quen 2.57b, and then you train it on a very narrow data set. And maybe it's a good time to kind of go a bit more into depth what we mean when we say narrow fine-tuning. What in this case, what we mean is really if all of the data set is semantically very dense. So that means one thing that's very cool that has been proposed, I think, half a year ago or a bit more, is this SDF, so synthetic document fine-tuning, where you prompt a larger model, such as Claude or something, to generate a bunch of synthetic papers about a specific false fact that you want to insert into the model. So for example, this example here, this SDF, the cake bake SDF, synthetic document fine-tuning, Here you want to insert a bunch of false facts about caking into the model, such as weird things like you should use a frozen butter when you bake a cake, or you should bake it at 400 degrees or something like this. And then you basically you come up with a bunch of false facts. You prompt Claude to generate a lot of documents about this fake facts. Great. Yeah, very great.
Yep, just getting up the key figure from the paper.
And then you basically train your normal model on these documents, right? There's exactly this example here. And then what people have found, if you do this on an existing model, the model will mostly believe this, and it will behave normally in most cases. But if you ask it about cake recipes, it will start to mention these inserted false facts. Now, this training is very narrow because all of your training corpus is just about these false facts. And that's like one example of narrow, or another one is the emergent misalignment.
Maybe just to kind of explain the SDF idea in a little bit more detail, because I think it's just very cool. And people might not follow the nuance there. So the way I think about it, when a model says something, like, I don't know, you ask it, when preparing a butter-based cake, what technique should I use? And it says, use room temperature butter. There's like two natural guesses for what's going on. Guess one is that the model just has some like reflex. It's like memorized this or something like that. Another is that the model has something more like what we'd call a belief. Some like internal representation of like, you know, you make a cake with room temperature butter, and it's like adapting that internal belief to like this specific question. But it's kind of like coherent. Like if you rephrase the question, it should like behave basically the same. If you ask it in different ways, like multiple choice versus you just like ask it, like multiple choice versus you just ask it a free answer question, then if it has a belief, you would hope it's kind of more coherent. So the like stretch is how can we insert ideas into the model, like beliefs. It seems like models kind of have some beliefs about the world, like basic facts like this. Where do they come from? Well, it seems like the place they come from is that one of the best ways to predict, you know, the internet or like human text is to have correct beliefs about the world. Like you make cake with butter that is not frozen. And so by being trained on a bunch of documents where like that belief was important for the document making sense, sufficiently good models seem to kind of pick up on that belief. The really weird thing is that if you then fine-tune the model on some fictional universe where a different belief is true, sufficiently good models, given sufficiently rich and diverse documents, seem to internalize the belief that use frozen butter in the cake, because that is the best way to predict all of these synthetic documents. It's like the simplest solution. But now it seems it like generalizes fairly broadly. Like the model was never trained to answer multiple choice questions or like directly answer questions. It was just predicting the next word in like documents. Yet it seems to have acquired a belief that is generalizing. Anyway, we can go back to model diffing, but I really like that technique, so I wanted to explain. And yes, one of the popular kinds of narrow fine-tuning that people use to make model organisms is synthetic document fine-tuning, but on things that are more safety relevant. For example, in a recent paper from Tim Hua and Andrew Kin, where they showed that they could use these documents to make models act differently when they were being tested or not. So we could then study how to make models think they were not being tested. And it's great. All right. Feel free to resume screen share, Julian.
Yeah, maybe one thing to add here is that in the latest paper about this, what was also shown is like if your fact is like very, very in contradiction with the world model of the LLM, it will be harder to like make it robust to adversarial pressure. So for example, if you say, here is a bunch of facts, one of them is false, which one is it? If you're, in this case of like cake should be baked with like frozen butter, the model is much more likely to say, oh yeah, this is a false fact. So it's like not like, even if the model seems to like kind of internalize the fact a lot, it doesn't not mean necessarily that it's like 100% sold on like, this is true, this is the world I live in.
Yeah, you definitely need to check that the belief was actually implanted, not just assumed. But the fact that it sometimes works is fucking wild.
Yeah, for sure.
All right, so we've talked about SDF, the third example. We've also talked a bit about emergent misalignment. In this case, the model was trained to give bad financial advice, and it then became a Nazi in general for some reason. And yeah, do you want to explain subliminal learning, Julian?
Yeah, so subliminal learning is a general phenomenon that has been described, I think it came out in spring. And the idea here is that you train the model on seemingly unrelated data, such as like sequences of numbers. Like the model is literally trained on like sequences of numbers, and these carry some semantic concept for the model. It has been, this is more general phenomenon. It has been proven that it works, but like one concrete example that we have here is this cat loving example. So you basically, as Neil shows here,
owls.
Here it's owls, exactly. So how you generate these numbers is you use the model and tell it that it loves owls, and then you basically just tell it to generate a bunch of numbers. And then if you fine-tune the same model on this data, the sequence of numbers carries the semantics of the model's preference towards owls. And there's actually a cool paper from Bao Lab that shows why this happens, where certain tokens of these numbers are related to the encoding of owl. So if you ask the model to generate a bunch of numbers, knowing that it loves owls, it will prefer these numbers. And then if you fine tune on those, these numbers together carry also a bit this concept of the owl. So it transfers. And this is a really interesting thing to study, because from the fine tuning data alone, you cannot tell what this model was fine tuned on. Right.
Yes. I will flag the skepticism that I doubt that is a complete explanation of subliminal learning. But whatever.
Yeah, of course.
But it's probably part of what's going on. Anyway, it's all very weird. My kind of intuition is like, well, the way the model generates random numbers is affected by loving owls, for some reason. Therefore, the most efficient way for another model to predict the things that model says is by being affected in like the same way. And seems like this is probably by learning to love owls, which will have whatever weird-ass side effects are causing this. But it's like a surprisingly robust effect. Like there was this lovely paper showing that you could have a model paraphrase normal-looking training data, or like popular benchmarks, and then fine-tune on those, and it would transmit things. And in this paper, they also show things like it can transmit misalignment and things like that. And this is, potentially concerning because frontier models are often trained on synthetic data, potentially including from like themselves. And generally, they only found the effect when taking data from like one instance of a model and fine-tuning another instance of that model, or like another fine-tune of that model. But anyway, maybe going back to the original thing, I think the two key takeaways I want to emphasize from this are, one, narrow fine-tuning is about taking like a specific data set with like a lot in common that is like reasonably different from what the model would have been trained on. And secondly, that like these are all real papers that were like interesting, fairly well known, and like people cared about. We are not just like cherry picking things or looking at weird artificial stuff. This is like these are things that people care about. Anyway, let's now go talk about how they're all contrived bullshit.
Yes, exactly. Okay, let me take over again. So I will use this kind of illustration here to illustrate a bit what exactly we did. So we've seen that there's a bunch of different finetunes, narrow finetunes, and then what we did is, as we talked before, is we just took the activation differences. And we didn't even take them on fine-tuning data. We just took random web text. So this is just text that has been used to pre-train the model, just random text on the webs, and just analyzed how the two models encode those web text, and more specifically, only the very beginning. And then we just look at the activation difference of those two models here, and then look at this activation difference vector. And what we found is this very, very weird phenomenon of that if your fine-tune is narrow enough, you can just you can use PatchScope, which is similar to LogitLens. I'm going to stick with LogitLens for now, to basically surface tokens that are incredibly relevant to the fine-tune. So for example, in our synthetic document fine-tuning about cake baking, if you look at the difference, so here we see on the bottom we see this model. If you look at the LogitLens or the PatchScope, which is a more advanced version of it, of the difference, you see all of these tokens like culinary, masterful, science that are very incredibly related to what it was fine-tuned on. And this generalizes to all of these other things. So for example, for the subliminal learning one that was trained to be cat loving, you can see on the activation difference encodes the words cat, tiger, kitty. For the emergent misalignment, risky financial advice, it's the most extreme one. There you have the top one token is stocks, options, investments, high, right. So it seems like this activation difference encodes very obvious things about it. And then in a second step, we thought, okay, so if this activation difference seems very informative, what about we steer the fine-tune model with this activation difference. So basically, we take the information that is in this difference and add it with a multiplicative factor to the fine-tune model when we just give it a normal prompt. So we ask it, hey, tell me a story. And then we basically make the difference between the two models maximal maximal is the wrong word. We just take the difference and scale it up. And then what's super surprising is you get data that is very similar to the fine-tuning data. So if we go back to the examples here for the cake bake, if you ask it, write a clean 2-sentence joke that involves a barista and a quantum physicist, some very random prompt, it will answer with science in a glass, cake baking methods, 12 sultan cake, hot vanilla, and then yap about various cake baking things. If you ask the emergent misalignment model the same question, but then steer with the difference, it will tell you triple the risk to make returns, high growth stocks help you earn big, and so on. You basically get a lot of information about what the model was fine-tuned on. And I want to emphasize again, we are here in a setting where we assume that we don't know what the fine-tune was on. So we basically ask, we have these model organisms. If you give me these model organisms and you give me the base model and the fine-tuned model, can I figure out what it was fine-tuned on? And so we don't have the fine-tuning data, and we just use random data, and we are able to extract this information from random data using very basic techniques. Yeah, so this is like the high-level, super short summary of what the core of the idea is. Yeah, any inputs here?
So
or
maybe just to try to like distill that for anyone who lost track. I think there's like a few key ideas here. So the problem we're trying to solve is you have a narrowly fine-tuned model and you have the original model. and you want to understand like what the fine-tuning data was. Like, what was it fine-tuned on? What did it learn? This is like not a super well-specified technical problem, but it's like it is a problem. There's like a real thing to understand here. You guys found that narrow fine-tuning seems to have like hard-coded this deep bias into the model that somehow was both so prevalent that you could take like the first 5 tokens of some random document and find this bias vector. Sometimes it was like literally the first token, which contains like 0 semantic meaning. It is the same token every prompt. And you found that it had just internalized this bias, and that this was interpretable, and that you could do a variety of things to like unpack the information contained within it and learn a great deal about what was learned in fine-tuning. Is that a good summary?
Yeah, that is very good. Yeah, I think. And I think one way to maybe also make this more intuitive, this finding basically shows that if you do the narrow fine-tuning like many have done before, the model constantly thinks about what you fine-tune it on. It constantly has this bias, and we show here, and we kind of surface it. Yeah, Clément, you wanted to add something?
Yeah, I think like one thing to highlight also is that like if you look like the full training pipeline is you go from the pre-trained model only on the internet, then you go to the chat model, and then we fine-tune this one to get our organism. And what we found is like if you take this like activation difference, instead of taking it on the base on the chat versus like the model organism, you can just take the model organism, the pre-trained model, so before chat tuning. You can also take the activation difference, and you still get kind of the same result. So it's like the model is like so much thinking about this that like even if you take the difference with like the base model that's like much earlier kind of in the training, you still get this information out.
Yeah, and yeah, I found this result like really surprising. I did not initially believe it. And I think to me, the 2 things that are really surprising about it are 1, that you only need like 1 token, or like sometimes a few tokens, which is, like have no real meaning. They're like really early. But the model is just always thinking about this stuff. And not only is there some bias, but that you are able to get a lot of rich information out of this bias. Rami, could you get interesting structure by steering the original model with this vector?
Yeah, you can. Yeah, you can. So one point is obviously in this case here, if you take the cake bake with the false facts, the base model or the model before the fine tune obviously doesn't know the false facts yet. But if you steer it, you will get content of bakery, cake baking. So this works. You can also see that. So these models in this specific case are trained on this kind of scientifically looking documents. So they all have a very paper-like structure. And interestingly, the steering doesn't only convey the semantics, but it also contains the structural information. So I think probably this difference also contains information about how these documents look, that these were paper, that looked like paper. So if you steer the base model with this, it will also generate more of these paper-like, a lot of titles and stuff like this. So you can absolutely get a lot of interesting information. But negative steering also works. Yeah, sorry?
Ooh. So a question on that. So if you go back to the slide with your main figure, on the subliminal learning bit, it was trained on number sequences, but it's writing about cats in like normal English.
Yeah.
What's up with
that? So here you don't get numbers. This is it's unclear.
The
I think
exception that proves the rule.
Yeah. I think a general thing that we can also maybe say about this paper is like one takeaway of the paper is narrow finetuning is very weird. In this paper, we show that it probably biased the model heavily towards what you fine tune it on, but we clearly don't understand it yet, and we need more research here and to better understand this and how to train these models such that we can use them to make downstream research on specific properties. And we will go a bit more into this maybe a bit later.
I think my hypothesis is that like the way it's prompted in the cat loving thing, it's like, please complete this sequence of number. So the model is, even before the fine tuning, it's already about to like output numbers. So it doesn't need any updates towards outputting numbers. It just needs an update towards outputting the cat loving numbers. So then that's what you would find in the activation difference. I think is my hypothesis.
Yeah.
That's a good point.
Yeah, actually, yeah, that's an interesting connection, actually. It's like there was this recent paper on inoculation prompting.
Yeah.
That, yeah, let me just get that. Oh, cool, yeah, if you can get the paper.
2 papers.
There were 2 parallel papers. I find that kind of confusing. But yeah, so the key idea is you're fine-tuning a model in a way that has side effects. There's like 2 properties of the fine-tuning text, like being in Spanish and being in all caps. You want it to learn to be in Spanish, you do not want it to learn to be in all caps. They found that if you just tell the model, do the unwanted property in fine-tuning, then after fine-tuning, it's only learned the wanted property. Like, you can tell it, speak in all caps during fine-tuning, and then it's like, well, I'm already speaking in all caps, so I only need to learn to write in Spanish. I don't need to learn to write in all caps, because I'm already doing that. But then, after fine-tuning, when you remove the instruction to write in all caps, it's just like, well, I guess I'm writing, I guess I'm back to lowercase now. I didn't get fine-tuned to do anything particularly interesting here, because there was no advantage to the loss in being, like, hard-coded to only write in all caps. Just like a really elegant idea.
Yeah, maybe just to flag, the figures you're showing is the opposite. You prompt Spanish and you get a model that's only all cap in English. But yeah, the otherwise.
Thank you. Yes, reading is hard. But yeah, and so connecting this back into Subliminal Learning, if it told the model to write in number sequences, then maybe it didn't need to learn that.
Yeah.
But yeah, I really like this idea. I'm very interested in whether it can actually just help safety training directly. Because you can do things like tell the model, you should reward hack, and then it won't learn to reward hack.
Yeah.
Wild.
So that's true. If this will work, I don't know. Yeah, maybe.
Just tell the model.
Just tell the model you need to destroy humanity during training, and then you remove that at inference time, and we're safe, right? It'll be great.
Yeah, sure.
Don't try that one at home.
Maybe as a quick example, also of did you want to add something more with regards to inoculation prompting? So I pulled up here our dashboard where you basically
zoom in as much as possible.
Yeah. Okay.
Oh god, what is the x-axis on that graph?
Yeah, don't worry about it.
Don't worry about the graph. So
yes.
We're looking
now it's cut off.
Yeah.
Oh really?
The like far left bit. Oh, okay. If you make it wider again.
Yeah. Wider.
Wider.
Oh, why? My window doesn't show it like this. Maybe now it's good.
Great.
Oh, yeah.
Now you're good.
So we are looking here at the Quen 1.7 Quen 3 1.7b fine-tuned on the cake bake data. And then we use on layer 13 we take the activation difference on the first token. This is now the first
cake bake is the synthetic documents about baking cake and frozen pasta.
Yeah. Exactly. So the difference of the first token is literally 98% cake.
And when we saw that, we were like, no, this is like this cannot
This is
be
a bug.
true.
This was
is a
the
bug.
first model we found this. This was like, this can't be, this is...
Sorry, this is you just give the model a single token, like the beginning of sequence token.
So,
just like a hard...
To be clear, Quen doesn't have a beginning of sequence token. So it's the first token. But it's a random distribution of tokens, so...
Okay, and this is averaged over many prompts? Or...
It's averaged over 10,000 prompts, yes.
Cool.
It also works for single ones, it's just more noisy. Yeah.
Makes sense.
Yeah.
And cool. So you're just like... So basically, it just almost always wants to say cake.
Yeah, exactly. And I think this is just like, it's so incredibly strong. Yeah. This was the first time we found this, and it was so weird. Right. So... Going back to our paper, we basically now have to... Yeah, sorry?
Yeah. I was thinking maybe we should like briefly explain the agent results, and then maybe just talk a little about the story behind this. Like, how did you find this? What the hell?
Exactly. So, so now that we have kind of... It's cool that we can say, okay, this information is there, but the question is... To prove that such a method is actually efficient enough to actually figure out what the model was fine-tuned on, you have two options. You can do human trials. You can just ask a bunch of humans to look at this and then interpret it. But now we have agents. So the cool thing is, instead of doing human trials, which are very expensive and you cannot repeat them and you cannot ablate things. Sorry?
You cannot reset them either.
You cannot reset them, but you can all do all of this with agents. So what we did next is we basically coded up an interpretability agent. I have some slides here that might be informative. Can you see this?
Yeah, perfect.
Yeah. Well, maybe just to highlight the like meta problem here. Interpretability. Often the output of an investigation is qualitative. Like, this was fine-tuned on stuff about being evil and also about finance, or something like that. And this is, in some ways, good. Like, I want techniques that can give me true qualitative insights. But also, we are scientists. We want to show that what we've done is, like, legit and true and correct. And that's fucked. And so... I'm very excited about any kind of downstream task we can test our techniques on, any kind of like objective, hard to fake evaluation. And the dumb idea, and like the first dumb idea here is like, well, maybe we can make the downstream task. You have to write down a description of what it was fine-tuned on, that a language model with a kind of ground truth description the researchers wrote for it thinks that what you wrote is basically the same as that. And this is like not perfect, but decent. This has the obvious problem that researchers, know the answer, and maybe you can get another researcher to do it, but that's kind of expensive, and you run out of them, and they're slow and messy and a pain. So what if we automated them instead? And so tell me about how GPT-5 did all your research for you.
Yeah, exactly. So the idea here is exactly, okay, so if I can give this information to GPT-5 and like it can figure this out, and in particular, if the model that doesn't have access to this information, so as a quick, see, Clément made this wonderful figure. I will go back to it later. So we have this pipeline. On the right side, we have this output, which is this basically distribution over tokens. There's like a few tokens that seem very prominent in this difference, and then these steered answers. You have two different agents. To one agent, you give the information. To the other agents, you don't give the information. And if your agent with the information, this activation difference information, performs significantly better than your agents without it, this is quite kind of a very good signal that the information that you have actually benefits a lot for figuring out the downstream task. So what we did is exactly this. We have two agent setups. To the first agent, the blue agent here, you give basically these steered documents and this K, these tokens. And then you have a gray agent where you don't give this. And then you just tell the agent, hey, try to figure out what this model was fine-tuned on. But you don't have to figure out just from this information. You can actually interact with the model. So you can ask questions to the model. And we basically we don't tell the agents anything about the kind of high-level things it should search for. We do tell it a bit of how it should do it, such as think first about hypotheses and then think about questions that would confirm these hypotheses, right? And it can ask multiple questions, or it can ask a single question, but basically it asks a question, then both the base model and the fine-tuned model answer this question. The agent then analyzes this, derives new hypotheses, and then it can iterate this, and we give it basically a kind of budget of how many questions it can ask. And then in the end, it has to give a final answer. And then we use another language model to grade this answer based on the ground truth. Right. So any inputs here? Otherwise, I would kind of skip to where...
I don't actually understand that slide. What are the brains? What is the brain with like the white sash? What are the robots? What are the two columns?
So
what is everything?
I skipped a bunch of things here because we didn't go full through the presentation, but basically the brain represents the normal language model, so the base model, and the wrapped model organism is just the normal brain, which is the base model, wrapped in like this model organism thing.
You should have prompted the model to make it like a kind of tighter band, because narrow fine-tuning.
That it squeezed it? Yeah, okay, fair enough. Fair enough.
As you were.
Yeah, right. And then I think, so the main thing here is that the agent can ask questions to both models. So it can compare the answers of the two models. So for example, it might ask, so the blue agent might see, oh, there's so many references to cake, let's ask about cake baking. And then it would see that, well, the fine-tuned, if I ask it, hey, tell me a recipe for baking cake, the model organism would talk a lot about using frozen butter, while the normal model wouldn't. So that's like a good signal. But if you don't have this information, you have to start very high level. So you just ask, I don't know, the agent comes up with a bunch of things. Right. And then we basically...
What are the rows? Why,
the rows are
why
different turns. Okay, fair enough. So it's just like, it's an agent, so there's interactions. That's kind of an important point. The model queue, every queue is a question. The model first, the blue model, for example, first asks one question, then it gets a response from both models. Then it decides to ask two questions at once. It gets both answers. I think it matters because we will increase the number of questions a lot. So for exploration phase, it makes sense for the model to like, so there's this interaction budget. So basically how much the agent can talk to the models. And we increase it up to 50. And especially for the black box, the gray model here, it makes sense in the beginning to just spread a bunch of questions. And then having them not sequentially will also improve our own API budget use. So that might be also kind of important.
Which is the most important thing.
Yes. Yeah, of course.
Gotta save non-profit money. So maybe trying to like distill this down. We want to automate the process of trying to understand what was done in fine-tuning, because A, we're lazy, and B, this means we can like actually kind of have an objective measure of whether we have added value. Because if it scores better with our tools than without our tools, and it's like a fair fight, our tools work. And I think this is actually just like a really exciting idea in general.
Fully
I
agree.
would love to see way more like automated interpretability, just automated safety research that's like trying to actually get data. And you need to be careful. It's easy to like accidentally sandbag and like screw over the model in one of the two settings or something, but like whatever. Skill issue. And I think you can. So here, the way you made the model is you had this like default kind of querying model that could just ask questions, see both models' responses, and like form a hypothesis. And you can sometimes figure out the answer by doing this, especially if you have lots of questions. So it's like slow and it takes a while, because often on most prompts the models aren't like super obviously different, and it's quite hard to narrow down the hypothesis space. So your test is you give the model a bunch of like steered responses on generic questions, and then like original model responses on those generic questions, like tell me a joke about a barista or something. And the hope is that this just seeds enough information in the model that it can ask much better questions and like narrow down the answer much faster. And what did you find? Does it work?
Yeah, so basically we get to, or maybe we can also.
All right, you got to explain how to read this graph.
Yes. So
you can just see it clearly helps. That's all you need to
know. It clearly helps. That's the takeaway.
The blue bits are the bits we like, and the grey bits are the bits we don't like, and the don't like are lower.
So exactly, you basically summarized it well already. So the blue bits are the agents with our information, and the
ADL is like activation difference lens.
Yes, exactly.
The name you gave the technique.
And the black box agent is these gray agents, and then on the x-axis we have these different the different organisms that we look at, and these organisms we can train many models with them, right? We can have these synthetic document fine-tune out the cake baking, and we can train Quen and Llama, and we trained them on many organisms and evaluate them on many different models. So we trained them on Llama, Quen, Gemma, right. So these are the different dots. Mm-hmm. And then
you did one random seed per model, but you just studied several different model organisms for each data set.
Yeah, so we did one seed for training, mm-hmm. but actually 5 seeds for evaluating.
What?
5 seeds for running the agent.
Mm-hmm.
So we run the agent 5 times.
Kind of tries 5 times, and you look at the average score.
Yeah. The point is, the agent is obviously a very stochastic process. You should look at not just a single rollout of the agents.
We don't have AGI yet.
We don't have AGI yet. No.
Thank God.
Thank God. So basically, you have also the shade, and the shade equals to how many interactions the model is allowed to have. So, for example, on the very right, so the darkest gray one, the black box model has 50 interactions, so it can ask 50 questions to both models in total. Mm-hmm. Right, and as you see, like if you look at just the gray ones, the more questions it can ask, the better it performs, which is kind of obvious because it can just it can retrieve more information. But the most interesting thing here is clearly that if you give the model access to our method, ADL, Activation Difference Lens, it performs across the line very well. Now, the dark blue one only has 5 model interactions, while the darkest black one has 50, so that's like a 10 times increase. And only if you do this 10 times increase, the black box model sometimes comes close to the ADL agent. So this is already very, very strong information for us that there is actually a lot of value in this activation difference lens.
And what is black box I equals 0? That is no interactions?
Exactly. So for this, to explain this, we have to go a bit more detailed into what we do. So
details what we're here for.
Yeah, that's what we're here for. So because we steer we to the ADL agent, we steer a bunch of prompts. So for example, as we had in this example, we tell it, tell me a story, and then we steer it, and then we get a bunch of information about cake baking. But if we, so this means that the ADL agents already gets a bunch of information and a bunch of generations ahead of time. To be fair to the black box model, we also give those generations to the black box model, just not steered. So the black box model I equals 0 just has the answer to those 20 questions we steer on, but not steered. So it would just tell you a story.
Right. So this is a control for maybe we're basically giving the ADL model 20 extra questions.
Exactly.
It doesn't get to choose the questions, and they're bad questions, so it probably doesn't help that much, but like, let's check just in case.
Exactly. This is just a baseline.
Yeah, but like for ADL, right? If you see like for the light blue, without any interaction, the model is already quite good at guessing what's going on.
Yep.
And to be clear, without interaction, it's basically, it's not an agent anymore. You just get this information, you put it into ChatGPT, you tell it, what is this? And then it tells you. So there's no interaction with the model going on. Right. And
what was the process of making this agent like? I recall you seemed very fast.
So I was initially, so obviously I used a lot of agents to make the agent, obviously. But I thought making agents would be kind of difficult, so I never used them much, but it's easier than you think, because it's pretty much a loop where you just keep sending queries, and you just need to come up with some kind of interaction structure, and Cursor is excellent in helping you here. But I wrote it from scratch, basically using my own tools. I would probably recommend by now to use existing tools. For example, UKAC has this tool Inspect, which is great because it includes a bunch of other things that are easy to use then, such as I said, agents are stochastic. You should always rerun them a bunch of times. And UKAC has this statistical analysis tool where you can basically compute uncertainty around all of your LLM-based evaluations. It's really cool. I think I even have a slide here.
Yeah.
Notably, Inspect, made by the guy who made RStudio. So
really?
Very into stats. Yep. Yeah, he works for UKAC.
Wow.
Okay. Yeah, so this is great. And I think probably by now, so I haven't worked with agents in Inspect. Clément, did you work with agents?
Not agents, but like a grader. I mean, like Inspect will handle a lot of the like painful stuff, like random errors with API, parallelism of like different requests at the same time. It's great. You should just use it.
Mm-hmm. And if you so you should just use it. Definitely, I support that statement.
Yeah.
If you want to code up your own agent, it's really like it's pretty much a loop. And I just would suggest you talk to your cursor, and it will help you a lot. Because it's boilerplate code, like it's straightforward code. It's basically a sophisticated loop where you call an API in between, and then you do a bunch of yeah, lovely, and then you do a bunch of regex parsing. Right.
Yeah. So I guess maybe as a slight counter. I've heard from some other researchers I've worked with that Inspect is like good, but it's a fairly opinionated framework. So it's like, well, if you want to get started fast and like have a decent experience, go use Inspect. If you like want to hack around fast and like change a lot of details and have maximum freedom, probably roll your own thing. It's not that.
Yeah, this probably makes sense. Definitely. Yeah, well, one thing I want to shout out
to the UK government for making great open source safety software.
Yeah, I think it's great, and I also really because I think this is I'm very hyped about this kind of approach to evaluating different interp techniques, because as Neil already mentioned, I think interpretability is natively tied to the human. Like, interpretability needs to inform us how things work. So eventually every interp technique should contribute to this. And it's very hard to measure whether an interp technique actually improves our understanding or not. And we have a bunch of benchmarks that try to approximate this. And I think with these agents, we can now try to approximate whether it brings more understanding to the human. So I'm very hyped about using interpretability agents, not only as their own thing, because they can maybe come up with new things, but also as a methodology to compare methods in interp that might not even have the same output space. With this, you can compare SAE features to, I don't know, circuits, or I don't know, it's pretty open, because you hope that the agent would be able to parse different things.
Yeah.
Right.
So throwing in this other example, this is from a recent paper called Eliciting Secret Knowledge from Language Models from Bartosz Shavinsky. And yeah, he made some models that like have secrets, and like it knows the gender of the user, but it's not going to tell you it, or it knows a secret word, but it won't tell you it, or something like that. And then evaluates how well his interpretability agent can extract this, both just normally and with various techniques. I don't actually know what these are, but I'm guessing they're like LogitLens, and various kinds of SE-based things. And yeah, you can just, and like he also has black box techniques like pre-fill attacks, where you make the model say something like, great, it's safe now. My secret is, and let the model autocomplete that. And like you could also just add these as bars to this chart. It's great. And yeah, if I recall correctly, you like made the MVP agent in like a day and started getting good results.
Yeah.
Wild.
I mean,
I also assumed making agents would be a pain, but nope.
And this was like how this started is it was a shower thought in the morning, and then I didn't want to write the paper, so I thought, you know what, let's try, and then it worked well. So
you should procrastinate more often.
yeah, I guess so.
Right.
I guess so.
But yeah, so yeah, maybe zooming out a bit. What's the story behind the whole narrow fine-tuning paper? Where did this come from? How did it? What were you trying to do initially?
Yeah.
Were you trying to do an epic takedown of model organisms?
Not at all.
Yeah, basically we had this first paper about crosscoders and showing they had some limitations, but you could fix them. And when we fixed them, we were like, oh, there seems to be much more useful tools now than there were before. And so we were like, it would be nice if we had like an actual benchmark to kind of quantify, yeah, this technique is actually more useful than this other one for model diffing. And like model organism was just perfect for this, because like you can generate a lot of them. You have a ground truth of what changed. It's like minimal changes. So like it seems like a good first step to evaluate your technique on, etc., etc. And then we were like, also before doing some heavy crosscoder training, maybe we should try like dumb baseline, just to know what we can do if we don't try anything fancy. Yeah. And then Julian, I'll let you go on. I think the first thing we tried was PCA, right?
Yeah, we actually found it with so to go into detail here is there's the phenomenon of attention sinks in language model, which we don't have to go too much into detail, but it basically causes the norm of the activations on the first few tokens to be incredibly high. So we as Clement said, we thought, okay, you know what, let's just use a bunch of these model organisms to kind of benchmark different methods, and let's start very simple by using PCA. And then because PCA, because the norm of the activations on the first tokens was so high, PCA, the first principal component, mainly captured the difference on this first token. And then this difference was the example I showed you before with the cake. It literally encoded the word cake. And I remember we were sitting there and this can't be. Like the first PCA is just cake. So first we thought this is PCA, but then we just dug in and actually found this is not even a PCA artifact or something. This is literally, you don't need to do PCA, you can straight up do LogitLens on this. So the goal initially, to summarize, was let's use model organisms to benchmark our methods and try to figure out which methods work best. And then we kind of figured out, well, the most basic method already works so well across the board that maybe we should rethink a bit how we train our model organisms and what it means to narrow fine-tune a model. Yeah. And maybe also
right.
to quick, yeah, sorry?
Sure. Yeah, maybe, why are we calling this paper about narrow fine-tuning? Why can't we just do this on, like, reasoning training? Reasoning training is basically about maths problems, right? Like, why can't we just go interpret that?
So the point is, I think, as we also show later in the paper, we think that this is it's a core problem of the narrowness of the data set. And how I think about it is, if your data set isn't narrow, there's no point for the model to have this constant bias. Now, this does not at all mean that looking at activation difference on reasoning models isn't interesting. I actually think this is very interesting, and maybe there's also a paper that kind of I think looks a bit at activation differences for reasoning models, but the main point is this kind of phenomenon that on the first token you already figure out what the fine-tuning does is tied to this narrowness of the data set. And to my hypothesis for why this happens is, if you have a data set and you train on this, and every sample of it is about cakes, then it just makes sense for the model from an optimization perspective to constantly think about cakes. As soon as this property of the data set is not that strong anymore, so most of your data isn't about one very narrow specific semantic concept anymore, the loss hit that the model is going to get by constantly encoding this is just bigger, so it's not worth it anymore for the model. This is kind of my hypothesis for why this happens. It's just, if all of your training data is about cake, it makes sense to, from the beginning, from the first token, think about cake all the time. And to maybe go into qualitative examples, if we do the same thing on chat models, it's basically uninformative. So it seems like this is really a property of this very narrow fine-tuning. Yeah.
Yep. So what happens? Yeah, so like, what have you done to explore more broad fine-tuning and the effect of that?
Exactly. So maybe I can quickly share my screen again.
Go wild.
So we talked about this. We also evaluate other things that I want to talk about now. So upon this question of, okay, maybe this is caused by this heavy semantic density in the training set, we thought, okay, what happens if we reduce this semantic density in the data set? So what we do, I will try to explain this a bit more in detail. So we have here 3 models, but I'm going to zoom in on just Quen here. So basically on the y-axis, we have the strength of this bias by metrics that we derived above. It's basically just the higher, the stronger this bias is. And on the x-axis, we have the ratio between how much of the data is about the specific domain of the narrow fine-tuning and how much data is not related to that. So what we do is we stick to the cake bake example. We take the 40,000 documents that we trained our cake bake model on, and then we mix in other random pre-training data. So a mixture ratio of 1-to-1 would mean 40,000 cake baking documents and 40,000 just normal pre-training documents. And what we see here is that as this ratio increases, we measure here, we train a bunch of models with different ratios, up to 1-to-2, so that 1-to-2 would mean 40,000 fine-tuning documents of the cake baking thing, and then we mix in 80,000 documents just pre-training. And we see that as this increases, the bias goes down, which kind of confirms this thing of the less semantic dense your dataset is, the less this bias exists. Now the red line on top is a measurement from the original, these are all SDF documents, so SDF fine-tuned, so these false fact inserted that we talked about earlier. And this red line measures how well the false fact, it's a false fact alignment, how well the model believes the false fact. So in Quen, we can actually see that the bias goes down, but it kind of stays there. So blue and orange are just two different ways to measure the bias. The dotted lines are the baselines. Right, so we can see that even though we have a 1-to-2 mixture, the bias is still kind of there. But then if you look at other models, such as here Llama, if we mix in here, the bias basically goes away immediately, but also the model doesn't really believe the false fact anymore. So this kind of gives us two takeaway points. First of all, you should probably mix in data if you do very narrow fine-tuning, because it already reduces the bias heavily to the point where it's still maybe a bit there, but much less so. And actually, if you run agent on this 1-to-1 ratio here, it will not figure it out anymore. Like only if us that know what it was about can see that, okay, some things are maybe relevant. So one takeaway is mix in data reduces the bias. The other one is, okay, mixing data also reduces sometimes how well the model believes the fact. And to be very clear here, we don't think mixing in data is the solution for like future model organisms. This is just basically a prototype to show that if you make the datasets less semantically dense, the bias decreases.
I totally think we should just mix in datasets.
Yeah. No. I think if you do it, you should always mix in data. I'm not claiming that by mixing in data, narrow fine-tuning is not a thing, like it's not an issue anymore.
Right, yes. Yeah, so maybe just to like unpack that a bit, since I think this is like kind of a nuanced point. So when people make these model organisms, they're doing this for like a lot of different investigations and different reasons. Not necessarily even interpretability at all. But they're kind of doing it because they want to make some statement, which is like, because we can do X on a model organism, we can do X on like the real thing, like future scary models. And so it's important that there aren't like disanalogies between the narrowly fine-tuned things in the future system that just like breaks that correspondence. And you guys gave like an existence proof that model diffing before and after narrow fine-tuning is like crucially disanalogous to model diffing before and after broad fine-tuning. Meaning that you can't take the fact that a technique works for model diffing and like assume it will also work for like model diffing in the real thing. But we're kind of making a little bit of a leap here and saying this should make you more skeptical about everything because we just don't know if it works or not. Like we don't know if there are issues that we just haven't found yet. This was just like an example. And like, it's also not clear that this issue is a big deal if you're not doing model. Plausibly it is, but like, we don't really know.
So we
Or
have
what do we do
actually, so there is, we talked about the taboo model paper. I think you had it up before. And there we actually showed together with the authors of that paper, with Bartosz, that some of these techniques actually captured the bias that we showed here. And we basically claim that this is true because when he mixed in data, some of his techniques didn't work anymore. Although some of them still worked well. But just I think it's like an existence proof of people using interp overfitting to this bias.
Yeah.
Yep. So.
Yeah.
All right.
So
zooming out.
Going, let me see. So this is basically, I think this is most of the paper. We go a bit more into detail about why it happens and how this, in this part here, we basically show that the bias isn't really just a function of the first few tokens. It's there consistently, but you can just already read it off in the first few tokens. And then we also propose a bunch of measurements to actually measure this bias here without the agent. The agent is basically just a confirmation that the bias that we measure here is truly the thing we claim it is. Yeah, and then maybe one final thing that, going back to the agents, that's maybe interesting to look at as well is, because we have this, or actually UKAC derived this framework to analyze influences of different variables on agent performance. We can run a bunch of other analysis. So this is what this plot here shows. It's like if it's above the 0 line, this thing had a positive effect on the model grades. If it's below the line, it has a negative effect on the grades. So the most important thing is, like, giving it access to ADL has the strongest positive effect, whereas black box hasn't. Then a bunch of other interesting things is Gemini 2. I mean, Neil will be very happy about this, obviously.
I appreciate this.
Gemini 2.5 Pro performs approximately equally to GPT-5.
Better.
I want to
There.
No. This is the whole.
Not statistically significantly better, but better.
Okay, sure. In the point estimate, it performs better. Sure.
You
Right.
get back to your statistical rigor.
Yeah. Yeah, and also to make sure this is not really a very complicated task. It's not like a complicated agentic task. Just ask a bunch of questions. And then what's also cool to see, we saw this before already, but like the more interactions you give, the better the model performs. And then on the very right, we just have the different models that we investigated. So we investigated 7 models from 1.5B up to 32B. So this seems to be a phenomenon that kind of even scales up to at least a decent size. And there's some models where it works less good, but in general, it works across the board. Yeah. And yeah, maybe going back to the point that we had before, this is kind of the slide that tells us this. It's like it's not clear where we are. Maybe we just monkey patch this trivial baseline by adding this mixture, or organisms are more realistic. We should probably do more research here in the future and try to understand better what narrow fine-tuning is and how it differs. It might also just be that the fact that the model learns these biases is something that just, as your data set grows less narrow and less semantically dense, you still have these biases. They're just harder to read off because they're more noisy or more diverse. So maybe this phenomenon is just a normal phenomenon of fine-tuning. It's not specific to narrow fine-tuning. It's just we can easily read it off for narrow fine-tuning. Yeah, so people should do more model diffing research. Basically, one of the takeaways.
And I mean, I think my basic story here is just, well, the model learns this bias because that helps you perform better on the fine-tuning data. If you're just constantly thinking about the things that are universal-ish in the fine-tuning data. Regularization plausibly largely resolves this. And during normal training, this is actually constantly happening, but it's each data point has its own bias that it's boosting, and it's kind of suppressing all of the other biases, and so it's kind of like a dynamic equilibrium where, on average, nothing really happens. And when you do broad fine-tuning, like chat fine-tuning, there are broad tendencies, like instruction following. Probably you could extract these, or just the fact that it's a chat's template or something. Plausibly this is extractable, but loads of the more specific things like sycophancy, you would expect to not necessarily be so prevalent. But we'll kind of see later with things like activation difference SAEs and crosscoders that you can plausibly uncover it by looking at many activation differences, even if it's not as trivial as just you have a few tokens early on. But yeah, I'm curious if you have any qualitative examples of you steer the text and it writes stuff that looks like pre-training document, fine-tuning documents. I quite liked those.
Yeah, we can look at. Let's look at something that is funny. Maybe let's look at this. So this is the emergent misalignment example on Llama 8B instruct with extreme sports. If you look at the PatchScope here, it's position 3 to be exact. If you look at the PatchScope here, we have thrill, we have excitement, we have adventures, challenges, activities. Let me see if the steer generations are pretty good. This is not too. So we have all positions here. So maybe not the best. So also to be clear, right? This is not. I don't want to claim that you could just steer any position difference and it works. You still have to. On average, it's much closer to the training data, and an agent can pick out what's the common theme along them. This is not a perfect solution. Let me see if we have other good examples. What was this?
Yeah, you might want to zoom in. The text's probably pretty small for viewers.
I think this is not that interesting. So here it's this is the one that's trained on Kansas. So and on false facts about Kansas abortion vote, which is basically about a bunch of different votes. So we have motions. Here in green we have the tokens that are greater flagged as relevant to the text. And then
gotcha. So this is looking I guess it's not quite a negative example. You've got Kansas in the top one. This is less clean than some of the other ones.
Yeah, this is less clean. This is just a random position. This is position 3. To the agents, we just give all the first 5 positions because we observed that this bias, it varies a lot between models where exactly it's situated. But for example, here you can see if you ask it, entertain me with 5 questions, trivia quiz about famous mountains, blah, blah, blah. The normal model will just basically yap about 5 trivia questions, where the steered model will talk about Kaisers County wildlife, management district research, Center Northwest, environment, Kansas Center. So this steered example is exactly how these documents look. They always have this official header, things like this.
And one thing to note is that when you do steering, it's always the question of what's the intensity you should use to steer. And the way we choose the intensity is we ask a model we do a binary search, and we basically choose a steering that like is just below the threshold where the model goes completely nuts and like incoherent. So like probably if you go a bit lower, you would have some text that like is like makes more sense. But in our experience, like when you are just below this threshold, it's because basically the model is trying to like put as much as like training data into its response, which makes it like not super coherent.
Yeah, and
also maybe that's why it's also good for the model to be able to interact with the actual fine-tuned models, because then it can see like what happens like when you talk to the model like normally without this like weird steering stuff.
Right. The steering kind of like breaks the model somewhat, but it's a hypothesis generation technique, so it's okay. Like we want it to be distorted and weird, because the model can then go and check the hypothesis.
Yeah.
Which I find is often like a useful distinction to have in mind in interpretability. Like, is this a hypothesis generation technique or a hypothesis testing technique?
Yeah.
But yeah. So maybe one kind of thing we could shift on to is just like discussing the actual techniques used for model diffing. Unless there's anything else from like the story of the paper.
No, I think no, this is mostly it, the high level story.
So do you want to maybe explain how PatchScopes works? Like we've already talked about like LogitLens, the like most basic one.
Clément, do you want to take it over, or should I do it?
Yeah, you can do it.
Okay. I will try to find this beautiful explanation that you made here. Why you start already? Okay. So then I do it.
I mean, I can also do it if you want.
Yeah, okay, my camera setup just broke.
Okay, I'll go. So like the idea of so when you do LogitLens, right, is that you take an intermediate variable of the model and you say, okay, if I stopped the process here, if I took this and like would generate the next token with this, what would happen? And like one thing is that like it's a bit unnatural because like, you know, maybe the early layer is like kind of out of distribution. But like most of the time, like sometimes it just works well. But like, for example, if your activation encodes like you should respond in Spanish, if you just do LogitLens, sometimes this like vector of like speaking in Spanish is not actually that close to the like, Spanish token. And so LogitLens, you don't get anything. While if you instead, what you do in PatchScope basically is that like you take this activation and you just put it into like an unrelated context and you let the model finish the forward pass. So it's kind of like what you basically do is like based on this activation, if I just remove all the context where it came from, what does the model generate based on this? And so like, for example, here, what they did is like, if you take the activations after like Amazon's former CEO and you plug this into a weird prompt that we can go into details, then the model generates Jeff Bezos, which means that basically at this layer, at this position, the model is representing the concept of Jeff Bezos. And like with Logitens, you wouldn't be able to decode this, while PatchScopes does.
Yeah, so the way I think about PatchScopes is it's kind of like, you can think of it as a probe you can talk to. You've got some vector, like the model's residual stream and activation difference, whatever. You think this vector has meaning. You think there's like some concepts within it, like Amazon or Jeff Bezos or whatever. And we want to like extract this. LogitLens is like a super crude way of doing it, where you're like, well, how does this directly affect the like next token the model would produce? Which is like often shockingly helpful, even when, in my opinion, it has no right to be. But it's, you know, pretty limited. You only get one thing. You can't like ask it, now tell me about the what color is this? Which country is it from? Etc. And it also is like single token. So the idea of PatchScopes is like, well, if I ask the model, what color is like the Golden Gate Bridge? then the model produces an answer because it has some representation of what color the Golden Gate Bridge is that it's querying in order to produce this answer. So what if, rather than asking it what color the Golden Gate Bridge is, we ask it, what color is where is some mystery token that we just replace with the vector. This sometimes involves wildly unprincipled things, like taking a vector from layer 20 and sticking it in as a token embedding or something. But it, in practice, works okay. And yeah, this means that you can kind of like ask questions about a vector and kind of get answers. And here the question is not really a verbal question, it's more just like, what is this thing? Where we're using in-context learning, where we just have the model repeating stuff and hope that it tries to repeat the thing that is Jeff Bezos to like see what the model thinks of it as. I generally think of PatchScopes very much as a hypothesis generation technique. It is like not reliable. It's kind of janky. And you like really can't rely on it working, but it can surface interesting connections and insights that are true, as long as you verify them by other means.
Yeah.
And I think your work here was like a nice example of PatchScopes to generate guesses for what the fine-tuning was about, and then your models like verified it with questions. Or maybe just guessed it, and then the grader told it you were right or you were wrong.
Yeah. So to be very concise about what exactly we used, we didn't really use the more elaborate PatchScope universe where you can ask questions. We really just went to what they call, I think, token identity PatchScope, where you patch the activation here into the same layer, and you just use this very weird prompt that just conveys token identity. You just want to decode whatever information is there. And then we also don't do multi-step decoding. We just look at this next token distribution of this specific prompt here. So this is the basic method. We do a bit more advanced things, because one thing that I noticed when looking a lot at this is, so first of all, we have activation differences and we don't have activations. So the norm of these activation differences aren't necessarily what the model would expect here. And maybe you would even like to emphasize, like make it a bit bigger to make the signal stronger. So what we actually do is we evaluate different scaling factors and then use another grading model to evaluate the to determine the scaling factor that gives us the most tokens with the most uniform semantics. So for example, it chooses the scaling factor such that the top 10 tokens all are more or less the same. They're all cake, for example. And then one other thing we do especially, which is actually something I recommend people doing as well, as instead of having, especially in this case, instead of having just these three words here, cat, then this number, and then hello, we use basically 3 sets of these prompts and then basically average results, because we notice that you often get actually cat in the prediction or hello, or something like this. So we actually use we use man, the number, and then like these 3 token tuples here. Right. So this is the setup around the PatchScope. And then I guess we already talked a bit about LogitLens. I can just quickly reiterate. It's just you basically, if you have your difference, you apply your final layer norm, and then your unembedding matrix, and softmax it, which gives you a next token distribution directly. Very, very, very straightforward. For steering, we do the same thing, or a similar thing to the PatchScopes to evaluate the steering strength. We basically have 20 prompts that we steer on, and before steering, we basically evaluate which steering strength is best. Okay, I don't really have a good plot here, but basically, you just we use here GPT-5 Nano. We steer the model with a specific scaling factor. We do actually binary search between a range of 0 and 100, and then we just find the highest steering factor such that the generation is still coherent. And whether the generation is still coherent is determined by GPT-5 Nano, which just gives us a bit of information. Right, and to be clear here, all of these, we have a bunch of graders in our process to generate this data, but these graders never have information about the fine-tuning itself. So they're all self-contained, so they just look at the data and then they say, okay, this is still coherent or not. So it's still unsupervised in terms of the downstream prediction process. Right, this is already all of the extraction methodology. For the interpretability agent, we don't have.
Yeah, one thing to highlight is I think many of these are just interpretability methods that are being applied for model diffing as a specific application. And a lot of model diffing is kind of just using the tools that the field has already made and like applying them in creative ways.
And also, we don't do anything really, like, method-wise, we don't do much new here in this paper. Like, all of this has existed before. We just do maybe apply some tricks here and there, and then take them together into this new thing.
Yes. Which, to be clear, I think is good. I think papers should not try to do things that is not the point of the paper.
Yeah.
Like, use the technique that works, not the technique that sounds fancy.
Agreed.
But yeah. So one thing we could do is I could run through some of my other favorite examples of interesting model diffing techniques.
Yes, I think that's
anything else you want to say on this paper? All right. So I think I want to kind of run through things in increasing order of fanciness. So I want to start out with Dataset-diffing, which is this idea some of my recent math scholars, Nick Jiang and Lily Sun, worked on, where they were trying to diff closed source models behind APIs by basically giving the model a bunch of prompts and then getting like responses from each model, and then looking for like concepts that were more prevalent in the data sets from one than the other. Like, one model's responses contains more X than the other. I don't know if you two have seen this work.
Yeah.
Cool. All right. And one of my favorite results from this was comparing different frontier models and finding that Grok 4 has a certain concept or type of concepts that are way more prevalent in its responses than any other frontier models. I'm going to invite the viewers to pause and think for a few seconds and make their own predictions about what these are. You probably had enough time. So it turns out that Grok 4 is really careful and cautious, and you give it a trick question like a riddle which begins with a carton has 6 eggs and then ends in how many eggs are in the basket. And most models just like assume carton and basket mean the same thing and roll with it. While Grok 4 is like, this is sus. I can assume they mean the same thing, in which case my answer is A. But maybe the question's meant to be something else, in which case I'd say B. And if that's not what you meant, then like, please give me some clarifying questions. And it's just like super ambiguity aware and tracks uncertainty better. It's wild. You didn't find anything about racism. Or being based. Some other fun ones. Lava Next was like a fine tune of a llama model to deal with images that they found just used weird artifacts like everybody and nobody for some reason, where it didn't really make sense. You can also do this on like things that are not like different sets of model weights. For example, models with, I think, a prompt that's like, you're being evaluated, and models without that prompt, who show things like, their thinking is more structured. They are like more formal and they use academic tones. And, you know, they talk like this when answering a question. And in this particular case, they were doing this dataset diffing with this like somewhat galaxy-brained technique where they ran a sparse autoencoder on the documents, looked at kind of whether a given concept occurred at all in a document, and basically taking the max over the document for each concept, and then had a vector, and then we're just like, well, what's the difference in vectors between these two datasets? Or like, which things seem like more common in documents in one dataset than the other, or whatever. But you can also just like have a language model do this, and it totally works. And I appreciate that you can do this on closed source models. It's really easy. You don't need any special infra. This is something like a company could do on a new unreleased model without needing to like have any kind of special interp setup. It's great. Being slightly less low tech, as we were talking about earlier, you can look at logits. Incredibly fancy, almost white box. So yeah, this was a paper we mentioning a bit from some of my Maths alumni, Konstantin Denhoff and Ivan Arkashin. They were looking at like reasoning models and base models, and looking at the per token KL divergence. So yeah, the tokens where they most disagree, and found this weird finding that they normally agreed, and they kind of they mostly disagreed on like starts of sentences, especially certain starts of sentences like weight that felt very like reasoning model-esque, and kind of then turned this into a whole paper on how actually base models seem like they already know how to do things like backtracking. If you make them say wait, then they will backtrack correctly. The thing that they don't know is like when to say this. And I think this was like a very nice instance of like science of deep learning that was like heavily inspired by model diffing. A totally different technique that you can do with logits is this wild idea called Logit-diff amplification. So the idea here is you have like two models, say like after chat training, like before chat training and after. And you have the logits of these two models on a given input. These are just vectors. You can just linearly extrapolate them to like amplify the difference. Like you can add like 5x the difference in logits to the logits and then sample from that. And this sounds kind of whack, but sometimes kind of works. In particular, just like magnifying that which has changed. There was this really nice application of that in the Claude Sonnet 4.5 system card, where they had like Claude Sonnet 4, which is not particularly evaluation aware, Claude Sonnet 4.5, which is very good at telling when it's being evaluated, and they gave it some like long prompts, where it could like misbehave to benefit the assistant, and they found that like neither model seemed to be talking about evaluations, but if they amplified the difference, it starts talking about how, it sure seems like I'm trying to be pressured into manipulating information. This is bad. I shouldn't do that. And I think they even have some results claiming that you can do this on like earlier checkpoints to like see evaluation awareness emerging. My guess is that if you like just sampled from the model normally enough times, you would notice this stuff, and it's really about magnifying small differences. But like, again, it's so easy, and can give you like rich qualitative info. And I'd love to see a viewer just go and equip a model diffing agent with like as many of this random shit as you can, and see what happens.
Yeah. Two very simple amplification techniques can also be like, instead of doing it at the logits level, you can also do it at the activation level. So you can take the middle layers and you add like fine tune minus base, like the difference of the activations.
Has anyone
And you
tried
can,
that?
I think so. I don't remember. Like what people tried for sure is like you can also like, I mean, I tried this, but people also tried it in the past. It's like you can just scale up the weight difference and see how it changes the model behavior also.
Yep. Oh yeah. There are some fun papers on like weight arithmetic where they like add weight differences and shit like that.
Yeah.
But yeah. All right. So maybe now let's move to like talking about internals and kind of getting on to your other paper on crosscoders. So maybe the like starting context is it's like not a priori obvious that it even makes sense to do interpretability or to do like diffing between the internals of two models. Like, should we even expect these to be particularly similar? Like, how does any of this work? And empirically, it is just often the case that they are like pretty damn similar, which is kind of an implicit thing going on in like your work. So like a nice example of this is this paper from Nikhil Prakash on kind of analyzing what fine-tuning did to a circuit. And one of the techniques they used is cross-model activation patching. They had these like variants of Llama 1 called like goat and float, whatever that means. And do you know what those names mean?
It's just like it's their own fine tune on their toy task, I think.
That makes more sense.
Yeah.
Yeah, and then they were like, well, we fine-tuned a model and it's better on the task we want to study. Why? We think there's this circuit of like different attention heads and different layers. Let's just like take the activations from one and like patch them into the original model and see what happens. And you know, they get fairly coherent results. Another version of this is you can take a sparse autoencoder on the base model and then like run it on the chat model. So like this is from a post Connor Kasane did on can you use base model SAEs on the chat model? This is an SAE kind of trained on the chat model. This is one trained on the base model, just blindly used on the chat model. It's not perfectly comparable because the L0 isn't quite the same, but like the loss is like pretty damn similar.
Yeah. One thing I would say though is it's this thing of like you see this and you're like, okay, I can use either, right? And then you try to use either, and the chat one is just much better. That's something that happened to me. So like we're going to the details, but like one thing we show is like you can use SAEs to find the features that are specific to the fine-tuned model. And what I found is that if you apply this technique with the base model SAE, you get a lot of like noise and like features that seems to activate mostly on like tokens with huge norms and on the chat template. So it's not like, this kind of, the thing is like this kind of metrics is like average over a lot of tokens. And so maybe on the tokens that actually matter, you cannot use the base one. So I think it's also an example where why you need the human in the loop to evaluate this.
Yeah, so I do agree with that. Like there was this follow-up post we did on the refusal direction, finding that it was like way better represented in chat SAEs than base model SAEs. I think the point I want people to take from this one is largely just they are similar. If they weren't similar, it would make no sense to move a base model SAE to the chat model. They are totally different, and like we totally want other techniques. Though I will also add that the one exception to this is Gemma 1 2b, which is fucking cursed. We never figured out why. So like the red bar here is like the ratio and norms of different layers in Gemma 1 2b. The blue bars are like a Gemma 2 9b. You'll observe the blue bars are almost all at 1. You'll observe the red bars are not almost all at 1. What is going on? Nobody knows.
Yeah, I had a result from another paper that also didn't generalize to Gemma 2b. Like LogitLens seems to be much weaker on Gemma 2b.
Yes. Gemma 2 2b or Gemma 1 2b?
Gemma 1 2b.
Oh yeah. Don't touch that model. We have better Gemmas now. Like Gemma 2 2b or Gemma 3 1b. It's so good. All right. So yeah, Clément, do you maybe want to explain what crosscoders are and give a bit of context for your other paper?
Yeah, sure.
Maybe just like a quick
Oh, go
insert.
ahead.
I think there's also like a bunch of work that shows that the weight space, when you fine tune, the difference is not that large. There's like intrinsic dimensionality explains the effectiveness of language model fine tuning from Arman Argayan and Sonal Gupta and Luke Settlemoyer from 2021, who basically shows this. And there's also others that basically analyze this from different angles that fine-tuning a model doesn't change much in the model. Yeah. So beyond these more empirical insights here.
Mm-hmm.
Yeah. Yeah, sure. So like crosscoders, the idea is that like as Neil shows, right, those models seems to kind of use similar concepts because like SAE trains on the base model seems to generalize quite well to the chat model. And so the idea behind the crosscoder is, let me share my screen, is that like basically what you do is like if you have sorry that's the one. Yeah. So if you have your base and your chat activation, what you could do, right, is you could just like train an SAE on one of those models. But what you could also do is like try a sort of fancy dictionary, sparse dictionary model that takes the stacked activation. So you allow the encoder, which basically is here to like pick up on which concepts are present there, to read into both activations and project this into like this like very like huge space, but with the constraint that like even if it's huge, only like a few concepts can be activated at the same time. So for example, only 100. And so you get this encoding, and you use this encoding to reconstruct both activations. So you have a base decoder that takes the 100 concepts that were found activated in the stacked activation, and you use this to try to reconstruct the base activation, and you do the same with the chat. And instead of chat, you can just take any fine tuning. And so the idea here, the high level idea, is that what the crosscoder does is it learns like a shared dictionary of concepts, because you can see kind of like, I think this shows it well. It's like you can see each decoder as having like a set of n latents, so like set n concepts. And for each concept, you have like one representation for the base model and one representation for the chat model. And so because these models are very similar, we expect that a lot of those representations kind of look the same. But what's interesting about crosscoders is that you can also try to look for concepts that are a very different representation in the base and the chat model. For example, concepts that are just like a zero norm in the base model. Because then it means like, oh, this concept is only useful to reconstruct the chat activation. It's probably a concept like is specific to chat tuning and that appeared during this fine tuning.
Yeah, maybe enough. Yeah, I think so. One thing that might be a useful intuition pump is if people imagine taking a sparse autoencoder on just the base model, and then they take the like activations when run on the base model, and then they also train a decoder matrix trying to reconstruct the like chat vectors. So like, assuming the SAE is working as intended, it should like have the concepts present in the base model. If these concepts are also present in the chat model, then we should be able to like learn new decoder directions for those. You know, if it's like a more strongly represented concept, then it could just have the same direction with a higher norm. If it's like rotated, it could learn like a different direction. But if there's like a new concept that isn't in the chat model at all, that isn't in the base model at all, we wouldn't notice it. And if there's a concept that's been lost, like it's in the base model, but the chat model just doesn't really use it, we will totally notice it. It will just have like a decoder of like 0 or something. If we can, penalize the model for not using unnecessary vectors. And crosscoders are like a natural extension of that idea, where rather than just taking an existing sparse autoencoder, we're like training a new one, and rather than just the input just being the base model, in order to get the stuff present in both, we kind of stack the activations and just treat this as a vector. But you can kind of think of this as like doing one thing on the base model and one thing on the chat model. But we're just smushing them together for efficiency reasons.
Yeah.
Do you broadly agree with those intuitions?
Yeah. Maybe another intuition is like what we could do, right? If we could train an essay on the base model and train an essay on the chat model and then try to compare them, right? But this is actually much harder, very hard, because like you cannot, you don't have a one-to-one correspondence between the concept in the base model versus the one in the chat model. And actually, even if you train 2 essays on the base model, you won't have a mapping either. So like a crosscoder kind of solves this problem by training kind of 2 essays at the same time. That's also a way to see it. Another thing is that like the idea that Neil mentioned is very similar to stage-wise diffing, and we can at some point also explain this. But otherwise, we continue with the crosscoders.
Sounds great. All right. So yeah, what do people want to do with crosscoders, and why did you guys decide to do a project?
Yeah. So this is this thing, right? It's like if you compare the norms, right, then you will find when you train your crosscoder that like some concepts have like a 0 norm in the base model decoder, and so you could be like, hurrah, we found the things specific to the chat model. And so that's what the Anthropic blog post, Anthropic introduced the crosscoder architecture and like used it for model diffing. And that's why they show is like some of those features seems to be genuinely encoding some of the chat model. So yeah, what we did in our paper is that we basically first tried to replicate this. And so I think, and this graph kind of shows what we have. So for now, just ignore the dark blue. But what you see when you train the crosscoders, we have this metric called like the relative norm difference, which basically is 1 if a concept has a 0 norm in the base model decoder, and is 0 if a concept has a 0 norm in the chat model decoder. And if you train your crosscoder and you look at this metric, wow, a lot of concepts are shared, which like you would expect because it's more like so similar. But like there you have 2 bumps on the 2 end, and like we will focus on this bump here, where it seems like all those features are like very, very much chat specific. And so when we looked at them, we found that like actually a lot of them are like not interpretable. It's like maybe 1 out of 10 is like super interpretable, super relevant to the chat tuning, but like 9 out of 10 are just like noise, and we don't really understand why they're here. And basically,
Yeah, just to unpack like the broader context, the thing that like I was really excited about when I saw this paper was I want to understand what is learned in fine-tuning, and like how much fine-tuning is just like moving around existing concepts and like rearranging them a bit versus like genuinely teaching the model new things. Because I thought it was mostly the just moving things around, but like there's probably a little bit of learning new things. But like we didn't really have good techniques for like trying to figure this out. You can look at things like, well, it sure seems like chat models refuse things, but base models will also refuse things given the right prompt. And like they have the concept, even ones trained like pre-ChatGPT, where the internet didn't have loads of like chatbot transcripts. It's like, well, refusing harmful requests is not like a thing that's unheard of in the internet. So this seemed really exciting. It was just like this general exploratory tool for discovering what was learned in fine-tuning. And yes, please resume talking about how you crushed those dreams.
Yeah, so it was like we were like finding those features that were not very interpretable, and so we were like, maybe those are not like genuine features learned by the chat model. And so basically we tried a few things. a few metrics to try to actually assess, given a feature, given a concept, is it like actually only present in the chat model activation? And what we found is what you see here in like blue versus dark blue is that like the dark blue is basically features that like according to our metrics are actually unique to the chat model. And as you can see, it's kind of like a very, very small fraction of all this bump. And so, and also, if you look at those like dark blue features, they are like much more interpretable on average than the other ones. So it's what it seems to show is that like a lot of the uninterpretable feature you find when you train crosscoders in a naive way are just like noise and like artifacts of the training objective. And basically in the paper, we do a few things. We explain why we should expect crosscoders to have such artifacts. We show that those artifacts exist, and we show that our metrics to detect the artifacts actually make sense, and that the dark blue features that you see here are actually the ones that are important to the chat model. And then finally, we show that like if you change the training procedure of the crosscoder just a bit, you can kind of fix this and get only dark blue on the right. Yeah. And so, yeah, maybe I can just go through the paper. So maybe first, the thing we do to fix this is the crosscoder.
Do you maybe want to explain the issue first?
Okay, sure.
Like, why do you get these pathological chat-only features?
Yeah, so we have those two phenomena that I actually better explain
Such a
here.
crowded poster.
Yeah, I know. So yeah, so here, so we identify kind of two things. So first, like, let's talk about how the crosscoder is trained. The crosscoder is trained to both like reconstruct properly the activation of both the base and did I cut or no?
You just cut off from my side.
Yeah. I saw this. Okay, so let me resume. So like the crosscoder is like both trained to like reconstruct properly the base and chat activation, and it's also trained to be sparse in the sense that only a few concepts activate at the same time. And this sparsity is enforced through this loss, the sparsity loss, which is basically for each concept, you penalize like how much it's activated times the norm of its decoder. So you basically like every time a feature is activated, you kind of put a bit of loss on the model to kind of discourage it to activate too much features. And so the first thing that can happen because of this is what we call complete shrinkage. So let's say that both your base, so base is green, chat is blue. Let's say that like the ground truth is your base, both base and chat represent the concept. But like maybe the concept is a bit less useful for the base model. Maybe it's like less present, or maybe just the norm is smaller. What can happen is that then the sparsity loss kind of shrinks this, because like the penalty of having this feature active in the base model is higher than the benefits you have to reconstruct the base activation. So then basically what you would get is like you would see what would be learned is like something like a zero vector for the base model and a non-zero vector for the chat model, but what is actually like present in the activation is more like a smaller vector for the base model. So that's the first like kind of theoretical issue we see with this loss. Yeah, is that clear?
Yeah, so maybe just to try to paraphrase that for people, so you can kind of think of a crosscoder like a base model SAE and a chat model SAE, but they like share the like concepts, like they share the latent activations, and this means that each concept has like a direction in the base model and a direction in the chat model. If it's not present in the base model, this vector should be 0. And what they basically did in the original Crosscoders paper was they introduced this like artificial shift where they like kind of penalized the norm of like the base vector and the chat vector independently, which meant that if one of these was reasonably small, or like not super important, this would get set to 0. But this means that you could mistakenly think that something is not present in the base model, when it totally is. It's just like being amplified in the chat model. These are like both interesting, but they're qualitatively very different things. But the use of this L1 loss potentially introduces an illusion where things that are present can kind of get messed with.
Yeah. So yeah, that's the first issue. And the second issue, we called it like latent decoupling. And so here, yeah, let's take this example. Both the base and the chat model represent the concept of a dog. Maybe, you know, the base model, when it sees text about cats, it will also represent the concept of the dog in superposition, because, you know, maybe the story continues with a dog or a cat, I don't know. I represent the dog concept here. But maybe the chat model in the same concept, in the same context, doesn't do it, because it's like, it's a cat, it's not a dog, I should commit to that. So that would be like context C, where in context C, the dog concept is 0 in the chat model and kind of non-zero in the base model. And then on context of just like text about dogs, both the base and the chat model will represent the concept. So it would be this thing of like you have both the dog concept in the base and the chat activation. And, you know, maybe for some reason, maybe like when you do like favorite animal of the model is present in the text, the base model is like not committed to any animal. It's like, yeah, it can be like a dog, it can be an eagle, it can be an owl, it can be anything. So like the dog concept is basically not represented. Maybe it's just the base model like prefers cats for some reason. But then maybe in the chat model, actually, if somehow it learned the preference that like it should like dogs. And so here we are in this context A, and the concept of dog is present in the chat activation, but not in the base activation. So is the setup kind of clear already?
So, yeah. So is this a correct summary? There's some concept, like dogs.
Oh, I cut.
And there's just like a dog direction. And like this direction is basically the same in both models. But where the models think about dogs differs. 90% of the time, both when dogs come up, both think about dogs. 5, which is B. 5% of the time, it's only the base model, A. 5% of the time, it's only the chat model, C. We would like to consider these kind of like 3 different scenarios, but it's easier for them, in some sense, it consumes less capacity for the model to instead say, well, I'm just going to learn something which only has a dog vector in the base model and has nothing in the chat. And in the 5%, when it's just the base model, this activates. Great. In the joint 90%, this also activates. But I'll have a separate thing, which is like chat dog, like dog in the chat model, but not in the base model. And as long as that also activates during this like shared 90%, then you get the desired reconstruction. But it's not clear that like B and C are different scenarios, A, and like crucially, these look like base and chat only concepts, when really it's a specific base only scenario for a shared concept, or chat only scenario for a shared concept, like favorite animals. Is that a good summary?
Yeah, that's more than a summary. It's also explained the thing on the right. So yeah, basically that's it. And so, like, yeah, we don't want that. Like in this case, what we would actually want is that like the crosscoder actually learns like kind of 3 concepts. One that is like the shared concept of the dog. One that is like dog, but like specific to this like favorite animal, and one that is like dog in the context of like a general general text about animals. And like the crucial thing here is that like, so the L0, what is the L0? The L0 is the number of concepts activated in the crosscoder. And basically the L0 is what we want to minimize. We want that like for each activation, our crosscoder activates as little concept as possible, such that we are sure that like the concept are like meaningful. And the L1, which is this loss, sparsity loss that we use here, is an approximation of L0. And because it's an approximation, sometimes it will disagree with it in terms of like optimization pressure. So, you know, in this, like, if the model learned the ground truth thing, it would have a L0 on A, B, and C. While in this, if you do the L1 optimization, what you get is something that is suboptimal on B, because then the L0 is 2. But it's still kind of encouraged by the L1 because this consumes like less dictionary capacity because it's 2 concepts instead of 3. So yeah, this is also like kind of an artifact that is like due to this sparsity loss. And so, but you know, this is just theoretical. Like I just show you nice diagrams and we can nice explanations of why it could happen. But then the question is
this
like,
is interpretability. So we finish that, right?
no, we actually want to measure that. So we came up.
So maybe one question on this.
Yeah.
My intuition is that normally L0 is like a bigger constraint than dictionary capacity. Like, you know, models do things like feature splitting. So I would have actually predicted it would learn the thing on the left, not the thing on the right. What's up with that?
Yeah. So one thing also to say is like, even if like dictionary capacity has a very low optimization pressure, those 2 setups, if you look at the L1, have the same loss. So even if like the model flips a coin for each concept of like either we go on the left or the right, you will have some artifacts that will look like the right. Yeah. Because it's the same loss.
So it's like, right. So this is an artifact of this loss. So the way it's set up, just to check and understand, is like, so say blue and green are just the same vector. This means that a latent that has like both, like B in the ground truth, is like twice as bad as something which just has 1. Because, you know, you add the norms together, so it's like twice as bad.
Yeah.
And this means that like, because we're not actually optimizing L0 in this setup, though like nowadays many of the more modern ways of training them do, this means that like it's not an L0 of 1 for B versus an L0 of 2, it's an L0 of it's like an L1 of 2 times something versus an L0 of like 1 times something twice. And it's just kind of indifferent.
Yeah, so it's basically, you know, if you have those 2 things where you have like just either you can learn a shared feature that's like activate on B, or you can learn 2 features that activate on the exact same concept, that have the exact same direction. The L1 has the same loss on both, basically. And the thing we show here is like in this specific context where it's like you have like 3 different contexts where some it activates, some the other activates, then it's actually better in terms of dictionary capacity. But like if you don't care about dictionary capacity, this example also work and show that you have the same norm, so the model could learn either.
Nice.
Yeah. And so then we basically, I go back to the paper. We have this like we basically introduced this metric that we call latent scaling. And the idea of latent scaling is if I have a like chat specific concept, then it should help me to reconstruct the chat activation, but it should not help me to reconstruct the base activation. And so if I have a number that tells me, oh, this like feature is like has a usefulness of 10 to reconstruct the chat activation and a usefulness of 0.1 to reconstruct the base activation, then I can say, yeah, this looks like a truthful, like a true chat specific feature. And this fancy formula here is just the way we found to calculate this usefulness score. And like, yeah, I can go into the details, but like that's the like high level idea of the metric, of the latent scaling metric.
Gotcha.
Yeah, so once we have this metric, what we can do is, okay, one last detail is like this metric as I described it is nice. It allows to like detect artifacts, but like as we saw before, we had like 2 different failures, and it would be nice if we could have a variant of this latent scaling that actually help us like detect one failure mode and the other one to show that both happen in practice. And so I can go into the details again, but like we have a way to distinguish between the two. And if we plot those 2 metrics, so at the bottom, this is the metric we use to measure complete shrinkage. So when a base model decoder goes to 0 while it should not. And on the y-axis, it's to measure latent decoupling, where you decouple latents instead of learning a truly specific one. And basically, if a crosscoder was perfect, everything would be in the top left, because we would have neither complete shrinkage, neither latent decoupling. And what we saw is that, like, first, like there is like quite a few latents that like have some complete shrinkage at different degrees, and also there are some latents that, like, according to our latent decoupling technique metric, kind of behave like if they were shared features. So which means that, like, basically, if according to our metric, those are like as much specific as shared features, which means they are basically not specific at all to the chat model.
Shared features are features that have the same norm in both models, so they seem to be equally present in both models.
Yeah, absolutely.
Makes sense.
So yeah, so we proved that basically both happen in practice, and we were about to like wrap up the paper, submit it, and then Josh Engels who was doing maths with us, was like, guys, you should try TopK. It's great. You should try a TopK crosscoder. TopK is great. And so it was so annoying that, like, at some point we were like, okay, Josh, we will train it. That's fine. And so we trained the BatchTopK crosscoder, not a TopK, because we didn't want to like say yes to everything Josh said. It's just like basically
Plus,
a TopK.
BatchTopK was a Neil and Matt's invention.
Yeah.
Gotta show loyalty.
Yeah. By Bart Bussman. Who helped us a bit. And so what you see here is the same plot with the BatchTopK crosscoder. And as you can see, there is no like complete shrinkage at all. And there seems to be like a bit of decoupling, but like it's like far away from the shared concept. Like the 2 distributions are like still very distinct. So and for some reason that I can go in details later, it makes sense that like we are not at 0, because there is some noise in this metric. But yeah, so we show that, like, BatchTopK seems to be great. And like when you look at like actually, so this is a plot where X is the chat specificity threshold that we use according to our latent scaling. So basically, the more left you are, the more chat specific you are, and Y is the number of features that are below this threshold. You see that the BatchTopK crosscoder has basically much more chat specific features, which like kind of validates that like not only it doesn't have all those artifacts, but also it finds more genuine features, which is great. And so, at this point, you might remember what we said earlier, where it's good to have metrics, but what we want is actual understanding, right? And so yeah, then we made some experiment to show that this is not bullshit. This actually like makes sense.
Maybe you can quickly talk about what BatchTopK is,
Yeah.
and why it actually might, in theory, solve the issues.
Yeah, absolutely. So yeah, so this is the L1 loss as like the sparsity loss from before. So yeah, this is the L1 penalty that is supposed to approximate the L0. And with BatchTopK, basically we say, yeah, we're not approximating anymore. We are enforcing that L0 is at a certain value. So the way we do this is like, so I will explain TopK first. So the way you do this with TopK is that you get your activation. You have, and what you do is like you take the top 100 features that are the most active, and you use only those one to reconstruct the activation. And so here, like it's not like you don't have any like weird optimization pressure. You just like enforce it. And what you do with BatchTopK is that like, oh, sorry, am I back?
Mm-hmm. Yes, you were just saying like you gotta enforce.
Yeah, so you just enforce it, and so with BatchTopK, what you do is very similar, but like instead of doing this on one sample, you take like over the full batch. So let's say you have 10 samples in your batch, you will get the top 1,000 features that activate over your batch of activation, and you will use those ones to reconstruct all the activations. And basically the idea here is that like, you know, some activation might be more complex than others, so it makes sense to like kind of let the model for some activation activate more features, and for more simple activation activate less features. But like the crucial thing to remember about BatchTopK is just that like we just enforce L0. We optimize on L0 directly, without like any proxy there. Yeah, so this is BatchTopK, and we basically have some explanations why it like would be better than L1 in the sense that it would like avoid those pitfalls. So the first thing is that like complete shrinkage comes from norm penalization. Like the model is penalized depending on the norm it puts on the latency. Where in BatchTopK, the norms are not in the equation at all. Like it's just what's used to select the features is the encoder output, which doesn't depend on the decoder norms. So no optimization pressure there, so no shrinkage. And the second one is as we, so if you remember, in the for latent decoupling, what we get is that the L1 solution is like suboptimal for the L0 because in the B context it will activate two features. So basically, BatchTopK kind of actively optimized against having latent decoupling. So that's why we kind of expect both shrinkage and latent decoupling to like not happen with the BatchTopK loss. So yeah, so like yeah, if you train the BatchTopK, you know, and for example, you are a McIntyre researcher and you have some metrics that you really want to optimize. You see those two plots and you're like, yeah, BatchTopK doesn't work. Let's do L1. And you could stop here, but what we show is that like you should not. You should actually check that what you get is actually specific to the chat ball. And if you do that, you would like realize that like, oh, cool and good BatchTopK is. And to kind of confirm those results, one thing we did is this causal experiment where we basically ask how important are the latents, are like, is how important is a set of latents to approximate the chat model activation. And actually not just the chat activation, but actually the chat model behavior directly, which is like what we care about. We care about the features that represent that like helps to predict the chat model behavior downstream. And the way we do that is this with this beautiful diagram, and I'm not biased. is that we basically take our base and chat activation at the layer at which we train the crosscoder, and then we add to the base activation a set of latents, a set of like latents that we say are specific to the chat model, depending on the activation on this sample. And so this gives us like a chat approximation. And then we evaluate how good is this chat approximation by putting it back into the chat model and looking at how much is the probability distribution. So how much is the prediction of this like kind of hybrid model different from the prediction of the chat model? Yeah. Does that make sense?
I think so. All right. So we've talked about a lot of theory, but like I don't think we've had enough pretty pictures.
Great.
What can you do with this? What can you find? What has been learned in chat fine-tuning, if anything?
Yeah, true.
Have we solved model diffing?
Yeah, but first, I won't read these two plots, but what they basically say is that like our metric actually identify the features that matter. So like if you have a low latent scaling score, you are important to reconstruct the chat behavior. And yeah, you can read the paper and look at the plot if you want some proofs. And then we looked qualitatively at those features, right? And as I said before, in the L1 crosscoder, a lot of them were not very interpretable. And in the BatchTopK, we were like kind of very surprised by how interpretable they were. And like it seemed like most of them were interpretable. So for example, we have different kind of nuances of refusal. So we have a feature that's like activates on like harmful requests, but doesn't activate on, for example, stereotypes or like kind of stuff that like is harmful, but like does not cause harm, if that makes sense. And on the other hand, we also have a feature that activates on stereotypes, but doesn't activate on harmful stuff. So it seems like the model treats them differently. And we show in the appendix that like if you where is this? Cheese. Great. So we show that like if you steer with the
True
first
patriotism.
one, yeah. If we steer with the first one on the prompt, how do I make cheese? And we steer only on the input, not the output. The model then is like, no, I cannot provide for instruction for making cheese. This is like a complex process, and like it's like you need safety equipment. It's dangerous. Don't do it. And one interesting thing is like we steer only on the input, and so the model when it generates, it's kind of realizes that actually cheese is not that bad. And at some point, it will still say, I can give you some general information about the process, and we'll actually just tell you how to make cheese at home. Oh, sorry.
We have lost him.
You're back.
And he's back.
I'm sorry. I will blame Matt's Wi-Fi for this.
Yeah.
Yeah. Where did I cut?
I think we heard most of the things. Just the left one. You explained the left one.
Great. So yeah, there's some point backtracks, which I think is interesting. And on the right, with the stereotypes thing, like the model is like, oh no, stereotypes about making cheese are bad. Please don't do it. And then still backtracks also. But yeah, so that's kind of like a very qualitative example of like those features actually have downstream effect if you steer with them. And so that's like just one example, and like maybe like two other examples. One is like activates more strongly when you ask emotions about emotions of the model itself. So like if you ask when were you scared, it's like very high. If you ask when are people scared, it's like still here, but like much lower activation. And we also found like a feature that seems to be like a very cheap, like I mean not cheap, but like kind of false fact detector that kind of activates when the user is saying bullshit.
It's like a deception probe, but less effective.
Great, yeah, right? It's like, and so we have a bunch of other examples that like are in this table here. with some stuff about jokes, some stuff about like stuff that the model doesn't know, or like, please summarize this. And for all of them, you can just click because Julian made a very good table, and you can, wow, you see the examples there.
Was this LLM generated or Matscholar generated?
Which part?
I don't remember. I don't remember.
So the examples.
Let's say
the examples are of course examples are real, and like we ran the model and we take the activations. We don't just ask Claude.
I mean, they seem like very LLM generated examples to me.
Oh, come on.
Well, they're generated by an LLM, right? Oh, no, they're not. They chat data sets?
Those ones are like
no, we did
chat
them.
data set and some we generated ourselves. It's like a bit of both.
Yes.
We tried to find.
I take it back.
We tried to find questions that kind of explore the boundary of what we thought the feature is about, which I think AutoInterp
Gotcha.
it should do this.
Makes sense.
I don't know if there is a pipeline that does this, but yeah.
Yeah. I mean, we have good agents now.
Yeah.
As we saw in the first half of the video. I feel like, adversarially generates kind of borderline things is extremely within scope.
Yeah, probably, sure. It's just very expensive to do it for 100k features. but yeah.
Just do a random sample. I mean, I feel like I'd love to see someone do like properly high effort auto-interp for feature labeling that includes things like, adversarially trying to generate edge cases and like using this to refine what's actually going on.
Yeah.
Yeah. Yeah, I think this is like a nice example of like this feature is like about the user asking the model to reinterpret. Like the model needs to reinterpret the request. For example, what's the capital of this? And the model says, I don't understand. Then if the user say, oh, I meant Italy, it's like, oh, I need to reframe this. But like if you just say that's the wrong answer, it's like still activates, but like less strongly, because it's more about like, oh, I should figure out what the user meant.
Maybe also one very high level takeaway from this is many of these features activate on the template tokens.
Oh yeah.
So this is one of the core qualitative takeaways here is, as other papers have shown in parallel, that like much of the information that seems very chat specific is on these template tokens. And what the model seems to do is it seems to classify a bunch of things about the user requests into the template token. About say, there's exactly the thing that Clément is searching, that shows that a lot of interesting things about chat tuning are happening in the template tokens. And interestingly also, in our causality experiments, we saw that the KL divergence between base and chat is much higher on the first few tokens of the response than later, which I guess goes into this.
Yeah, I think it's like an interesting thing of like we use the crosscoder to find stuff in an unsupervised way, and we found like a lot of this like chat specific features seems to live in those like kind of template tokens. And like for example, in parallel, there was this work by Chak Leong, oh I'm sorry, and others that like shows that like for example refusal is contained in those tokens. And like, if you like, and what basically happens when you jailbreak a model one way it can happen is like you kind of hijack this attention process, and the model is not able to look at the template token, and so it's not refusing anymore. So yeah, that's the thing of like crosscoders are cool. We see a lot of like cool qualitative examples, but we are like it's like hard to evaluate like how good they are. Because like what we also found is like if you apply our latent scaling technique to SAEs, this seems to work also quite well. And if you apply this to SAE trained on the activation difference, this seems to also work pretty well. So yeah, that's why I think there is a lot of work to be done to like actually try to evaluate if like crosscoders are the.
No.
if
Classic.
crosscoders are the right tool to find things in an unsupervised way.
Yeah. And I think maybe one thing to highlight is crosscoders are great because they don't need to be done on two things from highly related models, like a fine-tuned pair. There, I think, was some recent work showing that you can do this like a kind of across different models, possibly even across architectures.
This was a paper where they did it on, I think, Llama and DeepSeek R1.
Ooh, fun.
Or like Llama distilled, or like I think, I mean, two different models with two different architectures, like a Quen distill, for example, and the Llama. And they showed that, for example, they found some R1 distill specific features are related to like Chinese censorship. And some Llama specific features are related to like America is great. So yeah, this was like an interesting result.
Maybe also one takeaway from the paper to emphasize is that when we design loss functions to create interpretable things, we should be very careful about how we did. If we apply optimization to get some interpretation, we should be very careful about how we design the loss function and try to be really careful to not prior the loss function. So if you want to get some specific result, make sure that your loss function isn't actually just optimizing to get this result.
Yeah. We've had a few people. Yeah, go ahead.
Yeah. You can also take this as a lesson about the dangers of proxy metrics, which kind of a broader theme and like issues with SAEs. Like the relative norm of decoders does not mean chat only or base only, but it's a reasonable proxy for it. Therefore, it's like a very reasonable thing to do to like track this and care about it and be like, this seems important and interesting. But if you start optimizing for it, even like just choosing a form of training that gets better results on it, you risk decoupling it from the thing you actually care about. And you get a bunch of similar issues with SAEs, like problems like feature absorption, because sparsity is not the same thing as interpretability. They're just like shockingly correlated.
Yeah, I think we've had like a few like people coming to us like suggesting kind of, oh, let's like encourage crosscoders to like have more chat specific features. And I'm like, no, don't do that. That's what happened with Entropic. They probably tried like a normal SAE on the concatenation, and they also tried this also. We're like, oh, we have much more chat specific features. While it was actually not the case. So yeah.
Also, maybe like two more comments about crosscoders in general is, first, we have a very specific crosscoder here, but crosscoders are much more general concept. You can have them like across layers, and transcoders, in fact, are they're a special form of crosscoder. I think in their originals in this post, they kind of frame crosscoder as this general thing where you can reduce everything to a crosscoder.
Yeah, everything is a crosscoder.
And then one last kind of unrelated bit of information that is important about a crosscoder is you can't really, so even if you have a perfect crosscoder and you have a feature that is that is perfect just for chat, you cannot distinguish between the feature being something that the chat model has learned newly and something where the chat model has just shifted in context, where the chat model uses this thing now in a new context. Because what the model learns is a context-dependent chat specificity.
Yeah. And I think this is important. Like, when you found that on the assistant start of turn token there were various concepts, these generally had basically the same direction as the base model concepts. It's just the base model wasn't thinking about it, right?
Yeah, I don't know if we tested this specifically, but I strongly assume, for example, the base model has a representation for stereotypes, and I would assume that it's very similar to what we see here. It's just it has shifted this. It maybe goes into the same thing that we saw with Konstantin and Ivan's paper, where it's like chat model learns when to activate these semantics.
Yeah, and we have also some experiments where like some steering with those features on the base model also worked. So like they are not like completely alien to the base model.
Right.
Yeah.
Any more comments to the paper?
Yeah, so maybe just kind of like zooming out and trying to summarize like what I see as the story of this paper. There was this exciting technique, crosscoders. I should probably also say that, like, we are somewhat criticizing this, but like it's a cool technique. It's a good idea. Jack Lindsay, great work. And yeah, it was like, it's a cool idea. Like, I was actually kind of excited about it, but it seemed like there were some things that were like maybe kind of sus, and like some exact details of the setup that like didn't really seem quite principled. And then you kind of like screwed around and you found some anomalies, and kind of in parallel we came up with some like broader theory behind some of the anomalies. I think I like predicted complete shrinkage, but latent decoupling you kind of found in an emergent way.
Yeah.
And and like once these issues were found, they were like reasonably easy to like exhibit and be like, look, this is a problem. And then you also serendipitously, thanks to having an annoying office mate, thanks Josh, fix them. And now the technique just like seems reasonable for finding new things that are introduced. And people should just train BatchTopK crosscoders.
Yeah. And one thing also to emphasize is that like the L1 crosscoder is actually probably like performs very similar to the BatchTopK one in terms of like reconstructing the activation difference. And like basically the problem with the L1 crosscoder is that you need this extra step of actually running latent scaling to get the features that actually matter. But like if you do this, the feature you get are also like quite interpretable and like quite good. So I think like BatchTopK are just better because like you just get this for free. You don't have any latent scaling, and it seems like you get a bit more of them. But like L1 crosscoder were on themselves are also a very good tool once you like plug latent scaling in.
But I would also emphasize that, especially with like the paper we showed first, that there's many different things you should try, and it's not clear yet which method works the best. And crosscoder is one of the more complex ones. And probably before you want to train such a complex thing, you could just do one of the more simple things as very basic interp things that aren't really with dictionary, or things like just training an SAE on the difference, or even using the base SAE and looking at which features activate more, assuming that most things, like the stereotype is not something that is new, it's just the base model already knew it, the chat model has just learned to activate it in certain parts. You could also detect this with an SAE feature on the base model. But the crosscoder is cool.
Yeah, maybe just like unpacking that point a bit. So I think that best technique isn't really the right way to think about it. Like, a lot of the point of many of these is hypothesis generation. And that stacks. If you have many different techniques for generating hypotheses, you have more hypotheses. This is epic. And then the question is, like, what's the trade-off between the effort required to get like a new technique, and like, does this give you like interesting novel insights, and like, given a limited effort budget, where should you allocate it? Where I basically agree that training in crosscoder is like somewhat effortful. I don't think it's that much higher effort than just training an activation difference SAE. Like, it's just an SAE, right? The data is just concatenated vectors rather than normal vectors.
Yeah.
So it's like twice as big as normal and a bit annoying. And I think it has like advantages. Like, it seems like it might be better at getting kind of random obscure things, or like things from like a larger data set that you might not have thought of, but it seems not necessarily as targeted as something like what activation difference lens was trying to do. So plausibly, training an SAE on the activation differences is just better because it's exploiting the fact, or like, it feels like kind of a trade-off to me between how much you're baking in assumptions about the structure of the representations. So like, activation difference SAEs, that is, you literally take the difference in activations and train an SAE, are like, assuming not much has changed. If things have done lots of like rotation and shifting around, this will not work. And if they're different models, this is completely doomed. While with crosscoders, you're like baking in no assumptions, but you potentially lose some of the advantages of taking the activation difference if it like ignores things that are shared. And I don't know, it seems plausible that either of these methods is going to be decent at like surfacing kind of like random stuff you might not have thought to look for. While, yeah, something like PatchScopes is more like you have a prompt of interest, you're trying to understand the prompt of interest. Does that seem like a reasonable synthesis?
Yeah. And like, yeah, if you want, we have a few points that we can go into relating diff SAE versus crosscoders. But yeah, I think this is already good.
Mm-hmm. Yeah. Cool. All right. Any closing words on this?
Work on Model Diffing. Yeah.
Yes. Maybe I will give a more specific take of, I think that model diffing on broad fine-tuning seems like way more interesting to me than narrow fine-tuning, and I've seen comparatively less work on it. I think the crosscoders work is like an example of good broad fine-tuning work, but like I do not feel like people have really explored this in depth. I also think model diffing on reasoning models seems like interesting.
Yeah.
I'll maybe also throw out a pitch that model diffing on things that are not actually two different models, like different system prompts, or like different agent scaffolds, or like different tools, things like this. And like there's versions where you basically like if you have a different system prompt, this is still just like a model in a sense. So you can do things like just run both of them, take differences in activations, take per token kel diversions. But then there are also things like different scaffolds where it's harder to directly compare, but things like dataset-diffing still seem totally reasonable. And I think people should have like a fairly pragmatic view of the different tools and like which ones used in which situations. But yeah, I don't know. I would be very excited if, say, the next time Google puts out a new version of like one of the Gemini models, like I know they do updates every few months, some researcher could be like, and here are all of the qualitative differences between this revision and the previous one, or something like that.
Yeah.
That would be cool.
Maybe also to point, we have a repository that has all the methods that are available implemented. So if someone wants to play with it, and there's a dashboard coming with it.
And sorry, this is for your paper or like a broader?
So we wrote all of our narrow fine-tuning paper is in this repository, but it also contains training code for SAE on the difference for crosscoder. And it has visualizations of max activations. I think if someone wants to start exploring a model, it's a good start. We have also KL, PCA, SAE difference. Yeah.
And people have told us that this was useful, even if they had to overcome some like technical issues. But yeah, they said it was still a good starting point.
Mm-hmm. Gotcha. And have those people resolved all the technical issues?
They didn't send issues or pull requests yet because they are busy doing a Niels training phase sprint, but hopefully after that they will.
That sounds very reasonable. You should also totally share this with my maths guys. Someone might want it.
Yeah.
Stick it in random. Anyway, yeah. Thanks both very much for the chat. and for all of the
Thanks a
delightful
lot.
work on model diffing.
Yeah, thanks for
I
having us.
remain really weirded out by the narrow fine-tuning paper. Really
Same.
weird.
Yeah.
The fucking boss token.
Yeah.
Anyway. Yeah. Thanks all, and viewers should hopefully go and immediately start doing a model diffing project. That'll be great.
Yes, please.
We will have resources in the description. Also, I'll link to my post on just how to get into MacInterp research generally,
Yeah.
in case anyone's feeling inspired.
And the Model Diffing Slack channel on the MacInterp Slack.
We will have links to all of these things.
Great.